For our first circuit, we're going to be using the internal temperature sensor. So we don't actually have to plug in anything to any of the ADC ports. We're going to be using channel 16, which is the temperature sensor. But first we need to provide power to the analog power supply and the analog ground. So we'll connect pin number 12 to the minus rail or the ground rail. And we'll connect pin number 13 to the plus rail. So I'll have number 13 plugged into the positive rail and number 12 plugged into the negative rail. Let's go ahead and create a new project. I'm going to call this ADC tutorial. Okay, I'm going to make some pseudocode that I can use to tell me what I need to actually program. So we're going to do an ADC calibration. And then I'm going to select a clock source for the ADC. I need to enable the ADC. And then start the conversion. I think I want to put the conversion within the while loop because I want it to convert continuously. All right, let's start with the calibration. In calibrating the ADC, we want to make sure that the ADC is not enabled. And we can do that by looking at the register ADC1 and the control register for that, which is CR. This is the control register for the ADC. And we want to make sure that there's a 0 in the ADEN portion of that register. So we're going to use the AND equals and then the NOT. And we're looking for the ADEN bit from the register. So this should make sure that the ADEN or the enable is 0 or off. So now we can start doing the calibration. Calibrating it, we're going to go back to the control register. We want to write a 1 in the AD cal bit of that register. To make sure that the calibration is complete, we have to wait until there is a 0 on this bit. When we turn this to 1, we're actually telling the microcontroller to do the calibration by itself or automatically. And when it's done calibrating, it will make this part of the register, this bit, a 0. So we need to wait until this is a 0 before we can go on and do any other processes. So the way to do that is we're going to use a while loop, and we're going to wait until that bit is a 0, and it's under the CR register. And to test it, like you've seen in my previous videos, we would use the AND here, and we would test it with this particular bit. While the bit here is not equal to 0, it'll continually run, and then when it finally hits 0, it'll jump out of that while loop. If you take a look at the control register for the ADC, you'll notice that the AD cal bit is on the 32nd position. So if you had the control register is equal to, let's say, 1, and then you have 31 more zeros, that would be the 32nd position here. And the AD cal is 1. So this actually is the number for AD cal. You can see that it's a 0x8 and then the rest zeros. That's actually that number in binary, because it's at this position. So if the actual control register looks something like this, then because of this and this would be here, and the control register is here. So this and this, it's only looking at this particular position, the first position here, or the 32nd position here, and the 32nd position here. And that shows it would be false or 0, because 1 and 0 is equal to 0. But if there was a 1 in this position, because in that particular binary number for here, which is this and this would equal 1, because it's only looking at this position here. So this and this is equal to 1. The AD cal would be the mask. So this is the mask. So we're testing it to make sure that if it is not equal to 0, if it is a 1, because we put a 1 in it, we're going to wait until the microcontroller puts a 0 back into this bit to tell us that it's completed calibration. And we don't actually know when this is going to happen or if it's going to happen. So what if it actually gets stuck here? We don't actually know if we put a 1 here and it stays a 1 forever. We won't even know if the microcontroller is working or not. We can't really test that. So let's go ahead and put something on our LCD that tells us that it's working on the calibration. So let's first set our cursor position. And we'll start with 0, 0 position up at the top left. And then we'll send a string to that location. And we'll call it start AD calibration. When it prints that out and then it does the next thing, it'll erase whatever was there. You know what? I need to give me a time delay as well. We'll put about 500,000. 500,000 should be enough time to see that we have this string on the LCD. So let's put at the end of that string, or at the end of this process, AD cal success. So when it gets out of this while loop, we know that there was a success in performing the calibration. If you just see the microcontroller say start AD cal and then it just stays there for forever, you know that it didn't get past this while loop and we can start to debug that portion of the program. I'm going to separate this a little bit. And this is a lot of lines of code. Let's make something in the LCD functions that does this a little bit easier. I think I did something actually in previous. Yeah, I think I did this one here. Delay, yeah, string for character line 1 and string for character line 2. So let's go ahead and do that one. Let's use that instead of all of these lines. Send LCD send 2 lines. There we go. So the first one is here, first line, and then the second line is just really nothing. We don't need anything on the second line. Although on the next one, I can do that on the second line, success, when I need to specify a delay here too. So when it runs, it'll show start AD cal, but nothing will be on the second line. And on the next, after it completes this, it'll show AD cal success. Okay, so let's take a look at selecting a clock source. We first need to go to the APB peripheral clock enable register number 2, which is this one we're going to call in our code. And in that register, we have a bit that is ADC-EN, or analog to digital converter enable. It's bit number 9, and it shows in the description that this is the ADC interface clock enable. So we need to first enable the clock for the analog to digital converter. So let's do that first. And we want to write a 1 in that bit. I'm going to use the ADC1EN since we're using the ADC1 control register here. The next thing we need to do is to start the HSI14 RC oscillator within the chip. We have to select an actual clock source for the ADC, and the control register here has clock sources and has a clock source called the HSI14, and this is where you're controlling that particular clock source. The one clock source that the ADC uses specifically is the HSI14, and this is the bit we need to use to turn it on. We're going to enable the HSI14 clock. Once we enable it, the clock source will become live for our ADC to be able to use. RCC CR2. So let's go ahead and type that in. And we'll need to write a 1 in that register as well. And if you notice that there was a few other parts of that register that has a ready, and we can use this HSI14 ready to test to see if the clock has been enabled and is ready to function. So let's go ahead and write a while loop to make sure that there is a 1 written automatically into this bit by the microcontroller, because the microcontroller, when the clock source has been started, the ready bit will be written a 1 automatically by the microcontroller. So let's go ahead and create a while loop for that. And we're going to use the AND, we're going to use the RCC, the same CR2, and then the HSI, the ready bit. And we're going to make sure that we keep the while loop going while it's equal to 0. And when it becomes a 1, it'll escape out of this while loop. This is kind of the opposite of what happened in the calibration, because we wanted to make sure that the calibration, when we wrote a 1 to it, the microcontroller automatically wrote a 0 to it when it's been calibrated. We want to make sure we keep this while loop going until there is a 1 in this bit. So let's use our LCD. Okay, so we're going to start clock. And over here, we're going to say clock started. We haven't actually finished with the clock yet because we still have to connect the ADC to that clock, to the HSI14 clock. And to do this, we need to use another control register, which is called the configuration number 2 register. You'll see that there is a CK mode, and you have 3 choices, but we're going to be using the synchronous clock selection. Let's take a look at what selections we get when we type that in. So we're going to set it to 1 for the CK mode. So let's see what we get. So we get the CK mode 0, and CK mode 1. Let's see what CK mode gives us. And that is C. Let's see what that is. Control C. We have this number, and it looks like it's both 1s. So just by putting CK mode, we would actually invoke this selection, which is actually what I had in my test code, and it worked. So maybe I can try different ones and see what happens. So now we're finished with starting the clock. Now let's go on to enabling the ADC. Enabling the ADC is very similar to actually the starting up the clock. We have an enable and we have an enable ready. So we can test for a ready bit. So let's go ahead and go to the control register for the ADC. That's where the enable is located. And we know this because we used it up here. But now we're going to do the reverse of this. We're going to actually turn it on. So we're going to put a 1 in that bit and test to make sure that the ADEN is in fact ready and ready to do a conversion or start doing conversion. We can go ahead and test that to make sure the ready bit has been set. So we're looking for the ready bit, ADRDY, and that is in the ISR register, ISR ADRDY. And that needs to be equal to 1. So this is going to have a while loop while it is 0, and when it is 1, it'll get out of that while loop. So now we're turning it on and we're waiting for it to get ready. So let's go ahead and put our LCD in there as well to inform us if it is ready or not. So enable ADC, and then call it ADC enabled. We want to make sure that we provide enough time for the ADC to do its sampling. The way to do this is to go into the ADC sampling time register, the ADC SMPR. And we're going to be adjusting these bits here at 0, 1, and 2. And in this demonstration, I'm going to be using the slowest sampling time. So it gives us the most sampling time possible to do the conversions. So we're going to have to place 1, 1, 1 in the 0, 1, and 2 bits of the SMPR register for the ADC. So to access the SMPR register, we're going to our ADC1 and the SMPR register. And we're going to use the OR equals to write 1s in the 0, 1, and 2. We could just put in a binary number to put 1s in those positions from 0 to 2. But of course, there are macros already defined for us in the header file for the microcontroller. So we'll just use those. So we're turning on bits 0, 1, and 2, the SMP sample bits. Now we need to set the channel for the ADC, and this is the internal temperature sensor, the channel select register. And the one we want is number 16, because number 16 is the channel for the internal temperature sensor. But this is not the only thing we have to do. We still have to wake up the internal temperature sensor, and that has its own bit. And the ADC in the CCR register has a bit called TSEN, and that will tell the microcontroller to start the temperature sensor. Now the next line of code, I'm not sure if I really actually need it, but in the documentation it says to use this if you're using the temperature sensor. And it's the voltage reference, or VREF, and it's also under the CCR register. And you'll see that VREF enable is here. We are finally at a point where we can start converting. To do this, we need to start the ADC. So we're going to go to the ADC1 control register, and we're going to write a 1 to the AD start bit, AD start. And we need to make sure that the conversion has been completed. When we actually write a 1 to the AD start, it's going to start converting. And we need to allow the microcontroller to wait until it has completed that conversion. So we're going to create another while loop. And within this while loop, the condition is going to be in the ISR register. ADC1 and the ISR register is the interrupt and status register. Status is the key here. As we looked in the ISR register up here, we looked at the status of the ADC being ready. We're also going to look at the status of the conversion being complete. And that bit in the status register is the EOC bit, which means end of conversion. So when the end of conversion flag has been set, then we know the conversion is complete, and we can go ahead and grab the data. So let's keep this while going while it's 0, and then exit the while when it's 1. So where in this microcontroller is this data hiding. If you take a look at the data register for the ADC, you'll notice that from bits 0 all the way to bit 15, which is 16 bits, is available. The resolution has a maximum of 12 bits, so even though it's reserved for 16 bits, you're only going to be able to see 12 of those bits. But they use the 16 bits because you can actually left align or right align the numbers within these bits. And to do that, you can use the configuration register 1 for the ADC and select these bits. I'm not going to do that in this particular demonstration, but it's available to you if you find the need to do that. So we have the possibility of storing that data in some variable or just printing it to the LCD. That's what I'm going to do. I'm going to set the cursor location on the line 2 or the second line, and I'm going to send an integer to the LCD, and this is where I'm sending the data. And I'm going to give it seven characters for the length. I would like to put somewhere here on the LCD that the conversion has started, or showing that there is some kind of label showing that this is a temperature sensor. So on the first line, you will see temperature sensor, and then on the next line, you should see the data. Let's build it and see if it actually works. Looks like we have some errors here. Let's see what we did wrong. I used ACD, not ADC here. So all the way up here, the first thing I did. Looks like we do have one more error. Too many arguments. Should be integer here. Okay, I flashed the microcontroller, but I noticed that it was just giving me a blank screen. The reason why it did that is because I didn't put in these 2 lines of code to initialize the LCD and set up the LCD display. Okay, the microcontroller is flashed and you can see it's working, and it went through all of the initial verifications and validations. Let's take a look at that again. Okay, so it's starting the calibration, started the clock, enabled the ADC, and now it's reading the temperature sensor. You can see that it has a value of 1743 to 45, 46. I'm going to put my finger on top of the microcontroller to see if it changes. I'm putting my finger on it, and it looks like it went down to in the teens. Now, the 1712 doesn't really mean much in temperature, and I have to check to see if this is a valid 12-bit number, but we definitely know that it's more than 1024, so it's more than a 10-bit number. So in their reference manual, they actually have some code examples at the end of their manual. They show you a temperature computation code example, but in the documentation, they'll actually show you a formula to compute the temperature in degrees. And this is what this is supposed to be doing as well. So let's take a look at that other formula. And this is the formula that they say, calculate the actual temperature using the following formula. And this is the data that we're given. And it says to divide that by 4095, but we're multiplying it by the 3.3, or not sure what this actual number is, if it's the 3.3 or if it's the digital form of that number. We're taking that vsense we've just calculated and we're plugging it into this formula. And then we're using the average slope, which is the actual temperature degree change between the voltage references of 30 degrees and 100 degrees, but they don't tell you that here. And you add 30 degrees Celsius to it because that's what is computed at a particular calibration from the factory. So let's go back to the code example, and you'll notice that there are a couple lines here, defines, and these are calibrated. They actually store the calibrated temperature at 30 degrees and at 110 degrees. So they actually put a number and they store it in the microcontroller at the factory because every microcontroller is different in its calibration. You can use this in calculating the actual temperature. So we have the low and we have the high, and we can determine the average slope from these two numbers, computing it. And I think that's what they're attempting to do here. I could not get it to work successfully, but let's figure out how to get it to work for real. And we'll use the standard slope-intercept formula. So we're going to look up this number right here, Control C, and we're going to go back. And really, this is just for your information because you really don't need to go to this data sheet to find this information, but it does give you a good handy data sheet to maybe find other things that you might find that are very helpful or important. So you can see it says TS Cal 1. That's this temperature sensor, calibration 1. And there would be a calibration 2, but they don't list it in this data sheet, unfortunately. But it shows that the TS ADC raw data acquired at a temperature of 30 degrees Celsius. And here's the key. To improve the accuracy of the temperature sensor measurement, each device, microcontroller, is individually factory calibrated by ST. The temperature sensor factory calibration data are stored by ST in the system memory area, which is here, accessible in read-only mode, so you can't change it, obviously. And notice that they don't give you the other calibration. This one is the one for 30 degrees, but they're not providing you with the calibration for the 110 degrees. And I'm thinking, well, maybe this is an error in their data sheets, or maybe they only provide one bit of information for this particular line of microcontrollers. I looked in other data sheets and I did see both of them in there. And I did do some testing before recording this particular video, and I did notice that both of these values are in fact located in the microcontroller. And they would really have to be, because you need 2 points of reference to be able to find out a range and to be able to determine an average slope for use in a slope-intercept formula. So let's first take a look and see what these 2 values are. You'll see that in this program, they're using a pointer, and all they're doing is they're giving you access to that memory address. And the way they're getting the value in that memory address is they're using the pointer asterisk symbol to do that. Since the number is only a 12-bit number, probably, they're casting it as a 16-bit number. They don't really need the 32-bit number of that memory address, because the 16-bit number is sufficient and it's probably right aligned within that memory address anyway. So let's plug these defines into the program and see if we can access those numbers and see what they are. So let's go ahead and put it on the top of the program, and I'm going to take out these LCD lines because I only use these for debugging, and we really don't need these anymore because I know that they work. In fact, I noticed that this needs to be right next to the enabling. So right when we enable it, we need to turn it on. So these 2 things should be happening at the same time. And in here, I want to show some information here. So I'm going to just say temp. I'm going to show this number right after temp. So it's going to be on the 0Y, and then X, it's going to be 5. So let's put it at the 5th position. Or actually, I'd like to put a colon instead. And I'm just going to put an XXXX, because it's going to be a 4-digit number. I'll put this to 4. And over here, and this XXXX will disappear once the number takes its place anyway. So that's a good way to sort of reserve certain portions of the screen. So I'm going to put the 30 degree calibrated value, and that will have 4 numbers there. And then the one that was calibrated at 110. 1, 2, 3, 4. Exactly 16 characters. So let's take a look at this here. We're going to use this address and put it in another location. So this one is the 110. Let's start with the 30. So the 30 would be, we put the pointer symbol before that. So we're looking at the contents of the address, not the address itself. And we want this to be on the 2nd line. And let's see which 1, 2, 3, 4, or 0, 0, 1, 2, 3. So 3. And then the next one will be the 110 calibrated value. And this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12th position on the 2nd line. Let's take a look and see if we have a good compile. Okay, so we got a warning here. Oh, I had this in there when I was doing my research, so we don't really need that yet. Let's go ahead and do this again. Okay, no errors. So let's go ahead and flash the microcontroller and see what happens. Okay, success. So you can see that the digital voltage value is at 30 degrees is 1764, and at 110, it's at 1336. So, and we can see that our temperature is lying around 1728. So you can tell that it's closer to the 30 than it is 110, obviously, because it's not very hot in here. The chip isn't giving off any significant heat. Since this is probably going to be a linear relationship between the 30 degrees and 110 degrees and the 1764 and 1336, it should be a straight line between those 2 points. So let's see if we can draw something up and see if we can figure out this formula. Okay, so the slope-intercept formula is y is equal to mx plus b. Okay, b is going to be an offset. The m is the actual slope itself. M is equal to the slope, which is equal to the rise over run, which is also also equal to the delta y over the delta x. And all that means is 2 y positions and 2 x positions. So you have a line that has, a line is always going to have 2 points, and they're going to have 2 y's and 2 x's, or xy and then xy. So let's go ahead and take a look at a little graph. We should probably draw a graph and kind of understand what we're doing here. So let's say that this is temperature on this and on the y-axis, and the x-axis will be the digital voltage values. Okay, so let's take a look at the different values. Let's say that this is the 30 degree mark, and this is the 110 degree mark. And you're going to find this very interesting here, because you'd think that in the temperature sensing, you'd have the high value as the 110, but really it's the low value. So right here was, what was the number? Okay, it's 1336. That's the 110. So if you draw a line, we have our first point here, and then the other extreme is the 1764, which is our 30 degree mark. So we could actually just draw a line from here to here, and somewhere along this line is our actual temperature digital value. And you know it was somewhere around 1728 of 1727. So let's just say that that's somewhere around here. So where that meets here, that would be where that temperature is. We don't know what that temperature is, but we're going to figure that out. We're using the slope-intercept formula. So let's find out what the slope is first. So first we're going to take the difference of the y values, and the y values in this case is the temperature. So it's the difference in the temperature. So the difference in temperature is equal to 110 minus 30. This was correct in the data sheet. So this value would be 80, right? So we have our delta y. So our delta x is equal to the delta of it's actually the V30 minus the well, let's just call these voltages. The delta of the voltages, which is equal to the V30, which is this one right here, and this would be V110. Okay, so the answer to that would be 1764 minus the 1336, and that would be equal to 428. So then our slope will be equal to 80 over 428, which is equal to, I'm actually going to flip this around because I want to have a value more in line with the specifications in the data sheets, which is around 4.3, and that just means that I'm making this part the temperature. I'm just going to put that on the x-axis, and then the digital voltage would be on the y-axis, and that's just essentially me just rotating the graph around 90 degrees. So I'm going to make it 428 divided by 80, and that's going to be equal to 5.35. So for each degree of temperature between 30 and 110, there is a change of 5.35. If we divided it, this particular axis, and each one of these is 5.35 width apart, and that would be each degree on that scale. So now you know we can take the 1764 number right here and the actual data that we're getting from the temperature, and we can get the difference between 1764 and that temperature reading and determine what degree it is, because we have the number of degrees. We can divide that by 5.35. Another way to think about this is we're going over 5.35 and we're going up 1 degree. Going over 5.35 and we're going up 1 degree. If we did this the other way, like 80 over 428, let's see what that would equal. We get a value of 0.1869. So for each change in this number here, like this between 1764 and 1763, that would be 0.1869 degrees. That might actually be a little bit easier to determine. And the reason why I'm trying to figure this out is because I'd have to do extra work to find out where this crosses the axis and where this one crosses the axis, because we need to know where those cross the axis for the slope-intercept formula. And we really don't need to know that because we have what is a particular degree. So let's say we take the 1764 and subtract it with the 1727. So let's see what we get. So that would be 7, 14. So that would be 37 point difference. So if I multiplied 37 by 0.1869, that would equal the number, the amount of degrees Celsius. And that would equal 6.9153 degrees difference between the 1764 and the 1727. So if the 1764 is 30 degrees, and we added the 6.91, so let's plus 30 degrees to this, so that would be 36.9153 degrees. And that sounds like a reasonable temperature for my microcontroller within its environment. So I think at this point we have enough information to write our code. So first let's see if we can calculate a slope. We don't actually have to do that within our while loop. Our slope is always going to be set no matter what. That doesn't have to be recalculated over and over again. So let's find out our slope, and we're going to make this a float, and we'll call it slope. In fact, the data sheet calls it average slope, so we'll call it, I think it's called average slope. I'm just going to call it slope. So this is going to be equal to the difference in temperature, which is going to be 80. And then we're going to divide that by the difference between the voltage at 30 and the voltage at 110. And we're going to subtract that with the 110. So this should be our slope. Let's go ahead and see if we get the correct number. I'm going to go ahead and just delete all this, and we'll call it slope. So we're going to take one of these out since we don't need those numbers. We're going to change this to a 10. And we're going to display our slope, but we need to do it with a float. We're just going to do this as a new line. Floating point number. So this is going to be slope, and it's going to be 10 characters. And let's see, what? 6. Position number 6 on the second line. Okay, so let's see what our slope is. Hopefully we did it right. We don't have to keep showing this either because it's always going to be a constant. So we'll just show it from up here. And this has to be inside the while loop because it's always grabbing the data from the controller. And I believe when I'm dividing two numbers, I have to be very explicit with my casts, meaning that I have to sort of declare what this number is going to be. And I have to declare what this number is going to be. And in this case, I'm going to declare them as a float. So what I'm essentially doing is I'm telling the compiler what this number is going to be, and it's going to be a float, even though it really isn't going to be a float, but I want it to be a float because it's going to end up being a float anyway. So I want to keep all of the casts consistent, and this one also will be a float, even though it's just the number 80. So let's go ahead and try this and see if it works. And you can see that it does work. I can take away all these X's on the display. Okay, so now that we have our number, we have our slope, we can go ahead and calculate the final number. Because all we're going to be doing is taking our slope and we're going to multiply the difference. So we have our slope here. We can use it over here at least. We'll call it temperature. And that's going to be equal to the slope times the difference between our calibrated 30-degree temperature digital value. And we're going to subtract the ADC value of the temperature. So that's going to give the difference between from 30 degrees to the value of what the temperature is right now. So we're just finding what's the difference between those two, and we're multiplying the slope to find out what the degree difference is. So then what we can do is we can add 30 to this. Go ahead and make sure that order of operations are done correctly, because I want this slope to be multiplied by the difference here first, and then 30 is added to the end. So let's go ahead and see if we get the correct temperature. And we're going to want the floating point number here instead. So we're going to be displaying a floating point number, and let's go ahead and give it 10 digits as well. So let's see what happens. No errors. Go ahead and flash microcontroller. We should have around 36 degrees, and that's good. Looks like it works. Let's take a look at how we can look at an external voltage connected to a pin of the microcontroller. We might want to measure some kind of voltage coming into the microcontroller, voltage using a potentiometer, where we can take a potentiometer and use it as a voltage divider to bring in different levels of voltage between 0 voltage, which is ground, and to VCC, which is the 3.3 volts. So we're going to use this potentiometer to vary the voltage between those two ranges. On the microcontroller, generally the ADC is in this area. The voltage for the ADC is located here on these pins. Then the following pins in this location are where the input pins are for the analog to digital converter. When you turn the potentiometer, the wiper will either be on the top of the resistors or the wiper will be on the bottom of the resistors. What this is doing is it's changing the values of these resistors when you move the wiper. So in this scenario, you'd have the two resistors looking like this. And in this scenario, you would have a little bit of a resistor on the top, and then you'd have a lot of resistance on the bottom. So you have a large resistor top, small resistor on the bottom, and in this scenario you'd have a small resistor on the top and a large resistor on the bottom. And if the wiper is in the middle, like in this case, you'd have an even number of resistors in this voltage divider. You can use the Ohm's law formula to solve for this, but instead of going through all of the formula to figure this out, I'm just going to give you the voltage out is equal to the source voltage, which is 3.3 volts. And then you'll have there's two resistors in this scenario. There would be R1 and there would be R2. So to get the voltage output from in between those resistors, you have the R1 on top and the R1 plus the R2. So let's say that the R1 is equal to 0.5. like the wiper is near the top. We'd have 0.5 here. And I'm not using I'm just gonna say 0.5 ohms, just to make this simple. And the bottom we would have, let's say, 5 ohms. So we have half of an ohm resistance on the top here, and then you have 5 ohms resistance on the bottom. And that works out to 0.3 volts. Now let's look at a scenario where the wiper is on the lower end. So let's say we're using 3.3 volts, and the R1 would be the larger one, which would be, let's say, 5 ohms. And on the bottom, you'd have 5 ohms plus 0.5 ohms. And that works out to 3 volts. So you can see that is lower. And there's higher resistance on the top, but lower resistance on the bottom, that you have a higher voltage, closer to the maximum voltage you have on the circuit. You can never actually go over the amount of voltage you have. You can only go between the 3.3 volts and the 0 volts. Let's take a look at what pin we can use for the analog to digital converter. You can see that those pins are here. We've already set these up. We have the power going to the power rails, which is the VDD and the VSS. I forgot to put this one in. This is ADC. IN0. And I'm going to use this pin here, the IN1. The IN0 is really close to my power pins, and on the breadboard it's very difficult to get the potentiometer in that location. So I'm going to use the IN1. And at the IN1, we'll have that connected to the wiper, and we'll have the resistor, potentiometer, one end going to ground, and the other end going to 3.3 volts, the power rail, or VCC. The IN1 is pin number 15. So I'm going to take the potentiometer and plug it in right at that location. I'm going to directly connect these pins here to the power rail. But you might want to use a resistor just in case you go to one end. The wiper pin is actually on the back at this location, which is on the same tie strip as number 15. So I'll just take, it doesn't really matter which pin I go to, what ground or VCC, just as long as they're the opposite. So I'll take one pin and go to positive, and I'll take the other pin and go to negative. The programming for this is really simple because we've already created the code that we need to do this measurement. And all we're going to do is we're going to remove any of the temperature sensing code that we have in here. We won't need those anymore. This is actually the temperature sensor, the ADC channel that it uses. We're going to change that to channel 1. IN1 matches with channel 1 for the pin number 15. We won't need the VREF either. I'm just going to comment that one out because we may need that one at another time. And I'm going to remove the slope and the temperature. Let's see, maybe I can change it to something else. I'll call it pot or pot reading, potentiometer reading. And this one I'll just keep it blank. So we want the actual number to be in this location here. I can put a space after that since I have some room. We're not going to need this slope formula anymore, and we won't need to be specifying it on the LCD either. We won't need the temperature computation. So we'll put this is at this is X5, let's see. So we're going to put the sixth position here. And we actually need instead of temperature, we need the ADC DR data register. So we're just going to put the data register reading directly onto the LCD, which is the reading from the pin number 15, the IN1. So I don't see anything else I need to change. Let's go ahead and compile the code and see if we have any errors. Build failed. So it looks like I took something out maybe. Oh, I'm not using ADC, I'm using ADC1. We need to change that. Let's do it again. Okay, the build was successful. So the microcontroller has been flashed. It looks like I was off a little bit on you can still see an X there, but we can still take a look at the results. We use a screwdriver in the potentiometer, and I'm going to turn it up. We can see that the number is climbing, and you can see that there's the decimal and the zeros, and that's because I use the LCD float, send a float, not send an integer. Let's see how high I can go. I don't want to go all the way. I might have gone there. So I got a 3830 something reading. So if I go all the way down, I should go down to almost 0. I don't want to go all the way to 0. I went to 0. Okay, let's take a look. Let's get a closer look at this. Okay, you can see that the number is there. So I'm turning the potentiometer. I'm barely touching the potentiometer. I'm just wiggling the screwdriver. Makes it move quite a bit. And it looks pretty stable, actually. So you can see we got all the way to 4043 or something like that. 4040 something. And then all the way down to 0. So let's take a look at what a 4040 would be in a binary number and see what bit resolution we're getting. So let's take a look at the decimal to binary converter, and we can see that 4040 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. So we do have 12 bits of resolution. Let's let's do the reverse. Let's see. So let's take a look at a binary number with 12 ones. And see what that number is. So that's 4095. So we were pretty close to 4095. And there's going to be a little bit of resistance at some point in the voltage divider. Even the wires produce resistance. So I think we had a pretty successful attempt at using the analog to digital converter from one of the input pins. I'm going to demonstrate the use of timers and counters. In many cases, when working with microcontrollers, you'll need to use counters. And counters are connected directly to the clock source of the microcontroller. The microcontroller has an oscillator that's built in. And in this specific microcontroller, the default oscillation is at 8 megahertz, which is 8 million pulses per second. If you've been watching the LCD series, you know that there's already a place where I needed to use a counter because I had a time delay that was built in so the LCD would be able to wait long enough, or actually the microcontroller was able to wait long enough for the LCD to do whatever it needed to do to end its busy state. But we simply used a loop just to make it pause for a certain time frame. But that time frame was very inexact. It was not exactly what the datasheet called for. So in those cases, you might want to use the timers and counters because they're based on a specific value of oscillation within the microcontroller. If the datasheet calls for a pause for 100 microseconds, then you'd be able to specify 100 microseconds as a pause. We'll be getting into just basic counting with a prescaler. We'll be getting into input capture, which is bringing in a pulse and measuring the width of the pulse. We'll get into measuring the widths of the PWM signal coming in, and we can also output a PWM signal with specific periods and duty cycles. So let's go ahead and start with the first feature. I'm going to simply create a program that all it does is it counts to the maximum value that it has. And I'm going to change the prescaler to different values to see what actually happens with the speed at which this counts. When you're counting, you can count with a prescaler. The prescaler, all it does is it skips a specified number of oscillations in the internal CPU because the oscillations, you're oscillating at 8 million times per second, and that's a lot, and you might not want to count at that same speed. You might want to slow it down, so we can skip some of those oscillations and have it count, let's say for every 1,000 internal oscillations, it counts 1, and then another 1,000 internal oscillations, and it gets to number 2. 1,000 oscillations gets to number 3. In this specific demonstration I'm showing you here, the prescaler is at 1,000, and you can see how fast it is counting up to 65,535, which is the maximum amount or the maximum for a 16-bit binary number. The counter register that holds this number is only a 16-bit register. So let's go ahead and include the LCD functions. .h. When we're using the LCD, it's to initialize, and we're going to set up the display. Now we're ready to use the LCD. In this program, we're going to use the timer 1, TIM1. So the first thing we need to make sure is that the advanced peripheral bus has the timer enabled. And within that register, you'll see that we have some of the timers enable switches. The one we're going to be using is time1 enable, which is bit number 11. And the time1 is the advanced control timer. And the advanced control timer and the general timers are very similar. But we'll get into more of that later on. So let's go ahead and click on that. And you'll see that in the timer 1, advanced control timer is a 16-bit auto reload counter. And it allows you to use a programmable prescaler. And generally, most of the timers are very similar, and we'll get more into what the differences are later in these tutorials. But let's start off really simple and just use a counter and prescaler. So first we need to enable this timer. So we're using the clock control register and the APB2ENR. We're going to make sure we enable the timer 1 enable. With the timer, you have a register that holds the actual counter number, and that is called the TIMX CNT for counter, and the X can be replaced with the actual timer number, and in this case we're using timer 1. With a prescaler of 0 or no prescaler, the oscillator would look like this. The microcontroller is constantly creating a pulse, and these pulses happen 8 million times per second. So for each pulse, the counter with no prescaler, the actual counter register will have 0, 1, 2, 3, 4, 5, all the way to 65,535, which is 65,536 positions. And this conforms to a 16-bit binary number. However, when we're counting up and trying to show this counter on the LCD, it's going to go by so fast that you won't be able to see the numbers. In fact, it'll probably count up to 65,535 more than 100 times before it actually gets to the 8 million in 1 second. So that's where the prescaler comes in. So if we said the prescaler, we're going to shorten this to PSC, and that allows us to skip some of these oscillations. So let's say the prescaler is equal to 2. The prescaler has its own little counter, and it starts with 0, 1, and 2, 0, 1, and 2. So every time that it gets to 2, the counter will change. So in this scenario, with the prescaler at 2, the counter will have 0 here, and then 1 here. Let's go on just a little bit more. So the counter will count on every third pulse. So you have 3 pulses because it starts at indexed at 0, 1, 2, and starts again, 0, 1, 2, and it'll count for every 3 pulses of the oscillator. In the example that I showed in the introduction I had the prescaler at 1000, so it'll actually skip 1000 of these oscillations before it gets to the next counter number. The oscillations stay at a constant speed, it's 8 million oscillations per second, but by skipping 1000 of them, that means you have a lot more time between the counts. Prescalers are sometimes difficult to understand when it's being written in a data sheet. But really, if you think about it, prescalers are very, very simple. In a lot of features of microcontrollers, not necessarily this particular microcontroller, the prescaler is only allowed to be a specific number like 2, 4, 8, 16. It really confuses the programmer, but it really doesn't need to. I mean, it's as simple as just skipping oscillations. So let's get back to the program. So the next thing we need to do is set up the prescaler. To access the prescale register, we're just going to use time 1. That's going to be our main register for our advanced control timer. And the PSC is the prescaler register. And we're just going to make it equal to whatever number we want. And in this case, we'll make it equal to, I'm going to make it 10,000 this time. So it'll show a little bit slower on the LCD. And inside the loop, we'll access the timer 1, the CNT register. And all that does is it stores the actual count. Let's make this a comment for now because we need to show it on the LCD. We'll send 2 lines with a 0 delay, and we'll put on the first line the counter, colon, and on the next line we'll put in prescaler. So we'll display the prescaler that we're using. We'll set the cursor location for the second line, 10, 11. We use 11. And then it's going to be the second line, which is 1. And inside the loop, we'll set the cursor location, 10, and it's going to be on the first line. And we'll send an integer. And the integer we're looking for is the time 1 counter. And we'll make it 5 digits because it can't go up above 65,535. I forgot the 2 in the APB. All right, that worked. See if we can find it. Yeah, time 1. Okay. All right, it's currently showing the previous one that I had, so it should show 10,000 in the prescaler. So let's go ahead and flash the microcontroller and see if it works. And it did not work, and I think I know why. Let me take a look here. I forgot to actually enable the counter within the timer 1 control register. And the CEN is the bit that actually enables the counter. Counter disabled and counter enabled. So we need to enable the counter. So let's go ahead and do that. I'm going to put that right after the RCC. It's timer 1, control register 1. And we're going to, or equals, we're going to put a 1 in the bit for the enabling the counter. So let's try this again. Okay, now it works. PSC. And I'll make it 5 digits again as well. So let's build and then flash again. Okay, we can see that the 10,000 is in this space. So let's start playing with this number. Let's change the value of prescaler to different values and see what happens with this number. You can see it's moving up relatively slowly, but for every 10,000 oscillations, it is counting up each digit. So let's try the maximum number, 65,535. Okay, you can see that it's going up far slower. It's going to take quite a long time to get up to the 65,535 on the counter. So you can see what a difference the prescaler makes on the counter. So let's try changing the number to just 0 and see what we see. It should go so fast that we won't be able to see it. So you can see now it's just a blur. I mean, you can see it changing, and it's pretty obvious that we're not going to be able to get every single digit on this LCD because the LCD works very, very slow. So it's going to be skipping a whole bunch of digits, but it's just going to be putting at whatever the counter is at that particular time when the LCD is not busy. So let's try another prescaler, and we'll go with 500. Let's see if we can actually see the numbers change, or discern that is at least going in upwards counting. Okay, at 500, you can start to see it moving. Yeah, you can see that the numbers are counting up. So let's go a little bit farther down and try 100 and see if we can still see it. Yeah, you can still see it. I'm going to show you how to affect the counter's maximum value and how to count up and count down. Currently, we're counting up. What if we don't want the counter to count all the way up to 65,535? Maybe we want to count up to a particular number, like say 1,000. So let's go ahead and try to do that. But first, we want to make this number climb up a lot slower. So we're going to increase the prescaler. So let's do that first. That's 65,535. That's a 16-bit, the maximum 16-bit number. And another thing I want to do is, because we have that trailing 0 and the trailing numbers in the 5-digit number, I want to clear that portion of the screen so we can see the actual number of digits on the screen. So I'm going to clear it first. So I have 5 spaces. We'll make this the LCD send a string. And we'll take this 5 out of here. So it's just going to be putting in 5 spaces at the same location. And in that 5 spaces, it will put in the number. So let's see what happens when so we have the prescaler of 65,000. Build and slash mark. Get rid of those parentheses. Let's try it again. So you can see that we have the correct number of digits shown. And every time we are clearing the screen and then showing the number, causing a haziness. It's not allowing the number to show up for a long enough time. So let's put in a time delay, just one of our non-exact time delays, just so we can see this number on the screen. Okay, I'm going to put the time delay in just after where it displays the number. So it can display the number, have a time delay, and I'm going to start out with 10,000. Let's see what that does. 10,000 really is a very small amount of time. Okay, it looks a little bit better. The number looks a little bit more clear, but it's still kind of hazy. And it's really not necessary to see the numbers like counting up that fast. You know, our eyes are not going to perceive it anyway, so we might as well slow it down even more. So let's make it 50,000. Let's make it 70,000. Okay, that's far better. We will notice that the number is probably skipping a lot. We're showing the correct number at a particular time at displaying the number, but we're not seeing all of them. So let's see if we can stop this counter at a certain point. Let's stop it at 1,000. And then when it stops at 1,000, it'll start all over again at 0. So the register that we're going to be looking at is the auto reload register. And the auto reload register will contain a number, and that will be the highest number. You can also think of this as a counter overflow. So we're going to create the auto reload register, a number in there, and we'll use 1,000. So let's go ahead and just try this out and see if it works. Okay, so now it's climbing to 500, 600, 700. Should stop at 1,000. Okay, it did, and then it started all over again. But what if we want to count from 1,000 to 0? Let's see what we have to do. We can see in the timer 1 control register, there is a direction bit. So we'll access this direction bit, and it shows that there's a counter uses an up counter. This is the default value, obviously, because it's counting up. And the 1 in this bit, the counter is used as a down counter. So let's check that out. According to the datasheet, it says that the counter will start at the auto reload register, which is this, and it will count from this number to 0. Let's go to the CR1, and we're just going to add this to the end of this one here. So we'll go timer CR1 and then the direction. So we should have a 1 in that bit by invoking this macro. Okay, it looks like it started at 1,000, but we only saw the 900s. And it's counting downwards, so it counted down to 0, and now it's starting back up at the 900 to 0 again, 1,000 to 0. So that worked successfully. So let's look at a scenario where we can count up to the ARR value, which is the auto reload register value, and then count down to 0. And the control register gives us that ability to do what is called center aligned mode. So let's take a look at the datasheet again, and you'll see in C CMS, we have a few modes we can use. Edge align mode is the current scenario, which is 0, 0, and it is guided by the direction bit, which is over here. But the center align modes, and there are 3 of them, these modes focus on how the output compare interrupt flag is used when it's counting either up, counting down, or counting up or down. We're not going to get into that at this moment, but understand that you could have something counting up and then counting down and having an output compare, or counting up with an output compare, then counting down, or counting up with an output compare, and then counting down with an output. And we'll get more into that in later videos. But let's keep this one simple and just change the center align mode. And we can use any one of these, I think. Let's try it out. So we'll go with 0, 1, the CMS 0, 1. So let's see how we can do that. And you'll probably see that we have a few of the CMSs because there are 2 bits. Let's see if we can. So the 0 and the 1. So which one is in the 0's place and which? So the 0 place is the one here. So we want the 1 in the 0 place. So let's use the 0. So let's see if it counts up and then counts down. Good, we have no errors. That flashed. Let's see if it worked. Okay, it's counting down, then it counts up, and it counts down. So we are getting a zigzag, counting up, then counting down, and then counting up and counting down. So we do have the center align mode that we were looking for. I'm going to show you how to output PWM signal from the ARM microcontroller. PWM stands for pulse width modulation. So in pulse width modulation, you need a pulse from 0 volts to some other voltage, let's say 5 volts, and you need a width, and the width specifies the width of the actual pulse, and modulation, meaning that you can change the width of the pulse. The pulse width modulation, the PWM signal, is a way for a digital signal to output a specific voltage other than the specified voltage of a standard digital signal, like 0 to 5 volts or 0 or 3.3 volts. In digital signals, you generally can only have either the 0 volts, which is ground, or the 5 volts, which is the high value. And then within that digital signal, you'll have, say this is 0 volts and 5 volts, you'll have a threshold in the middle that is considered like the no man's land. So if you have a 0 volts and then you change it to a high and it doesn't get quite that high, and maybe it comes up to a high because of some physical phenomenon in electronics, and then it finally gets to that high. This portion right here is not considered any signal at all. It's just another state that would not be recognized. And the microcontroller would maybe default to a specific 0 or 5 volts depending on how the microcontroller operates. But to make a, let's say, a digital version of a 2.5 volts, you wouldn't be able to do that just with a digital signal. You would need to be able to pulse the digital signal so it is outputting a 2.5 volts, turning the digital signal on and off very fast. For example, if I was going to pulse on a line like this, the pulse is equal width as the width of it not pulsing. So if this is a 0 to 5 volts, this would equal 2.5 volts, depending if the pulse was fast enough to provide an output that is discernible by a meter, or even maybe if you're dimming an LED, it would be fast enough so you wouldn't see the actual flickering. And that's where a couple of the aspects of pulse width modulation come into play, and that is period and duty cycle. I'm going to draw a larger pulse width modulation here. In this pulse, the period is measured from where the pulse begins to where the flat part meets the next pulse. And the duty cycle is the percentage of the width of the pulse in relation to the period. So this would be a 50% duty cycle. Let's take a look at a couple duty cycles. For example, you'd have a 25% duty cycle if the width was 25% of the period. So if each of these graph lines, there would be 4 parts within 100% for 25%. And it would continue this way until you've changed the width of the pulse. So it would be 5 volts times 0.25, which is 25%, and that would equal 1.25 volts. In the 50% version over here, this would equal 5 volts times 0.5, and that would equal 2.5 volts. Another example would be 0.75, and this would equal 5 volts times 0.75, which is equal to 3.75 volts. And the reason why the voltages equal the voltages they do is because this is 0 volts, this is 5 volts, and you'll see, like in the 50% example, it is 5 volts for 50% of the time. time being the period, and that it is 0 volts the rest of the time. This being a pulse width modulation signal that's fast enough, you would discern this specific voltage, say on a multimeter or watching an LED being dimmed. So 5 volts would, for an LED, would be its full brightness. 0 volts would obviously be off or not showing any light at all, and 2.5 volts would be between that. In the 25 volt version, you can see that at 5 volts, it is only on for 25% of the time. So it's not on for a very long time, and it's off most of the time, which is 75% of the time it's off. So it's obvious that the 1.25 volts would be closer to the 0 volts rather than the 5 volts. And the same is true with the 75%. It's on more of the time. It's at 5 volts more of the time than it is at 0 volts. So you'd have 3.75 volts of output in this case. So what registers do we have to adjust in the ARM microcontroller to achieve a pulse width modulation? The first one is the timer. We're going to use the timer 1, the ARR register, which is the auto reload register. That was the one we can specify the maximum number of counts before it went back to 0 count. Like when it was in the up counting, it would go from 0 to the ARR value and then back to 0 and start right all over again. It would look like this, counting up to a particular point, and then it would stop and start all over again. Counting up, go back down, counting up, and going back down. The ARR determines the period, and the duty cycle is determined by the timer CCR register, which stands for the capture compare register. The one after the CCR actually corresponds to the channel that we'll be using to output the PWM. This is something I actually got wrong while I was testing the programming off camera. So whenever you see me using CCR1, you'll actually need to use the channel that you will select to output your PWM. And just like the ARR register, the auto reload register, the capture compare register is a 16-bit register, and it'll accept a number just like the ARR register will. And you might be able to surmise that since it is, or the period is determined by the ARR register, that the period is also dependent on the counter. It's based on the counter, not the actual oscillator that's in the microcontroller. So you have a little bit more control, and you can cause the period to be relatively long because you can use a prescaler to increase the number of times the oscillator is skipped for every count. Let's take a look at some examples. Let's say that the oscillation, or the oscillator, pulse of the oscillator, looks like this. This is the base oscillator that's within the microcontroller, not the counter. And you specify that the timer 1 prescale is equal to 2. So right there you know that the counter is going to be considering this would be 0, 1, and 2. The count would happen like this. The count would actually skip, would happen on every 3 oscillations because it's based on a 0-based index. Some devices require PWM signals to be relatively slow, like in the servo motors that I demonstrated in the AVR series. And some devices, like laser power supplies that determine the intensity of a laser, requires a PWM to be relatively high. Some devices are very loose in their requirements, meaning that you can have a large range between periods, widths of periods. So you can have very slow to very high PWM signals due to its tolerance. And there are some devices that require precise periods for their PWMs, because they may actually have circuitry that will measure the PWM to determine a value, especially when that device is an instrument that requires extreme precision and resolution. This type of PWM that I'm demonstrating here is called the edge-aligned PWM, meaning that the period starts at the edge of the PWM signal. You also have center-aligned modes. That was also called phase-correct mode in the AVR series, but we'll discuss that in a later video. So where does this PWM out? The timers have channels, as you can see here. You see timer 3, channel 3, timer 1, channel 2N, timer 3, channel 1, timer 1, channel 2, timer 1, channel 1, timer 1, channel 1, channel 2, channel 3, channel 4. We have a timer located at pin 44, which is timer 1, channel 4. The pin that I want to output the PWM signal out of is pin number 44, because these pins 43 and down, these are being used for the LCD. So the one that I have immediately available is pin number 44, which is the timer channel 4 at my disposal. So there's probably a couple things we need to do. We need to make sure that the alternate pin function is used for the pin number 44, because we don't want it to be used for general purpose IO. We want it to be used for one of these, specifically the timer 1 channel 4. So let's take a look and see how we do that. Let's let's go to the data sheet, the reference. And the way you select the pin that you want to use is the CCMR1 pin, which is the capture compare mode register. And that's kind of misleading, but the electronic engineers out there will probably find that this is a normal thing. So you can see that you have output compare 1, output compare 2, and you have these PEs and FEs and CEs. And these are explained underneath the table, specifically for like the CE would be clear enable, the M would be the mode, the PE is preload enable, FE is fast enable. And as we get deeper into using these modes, these will be explained. The hint that this particular register has to do with the output or the input channels is that in the description it uses the channels can be used in input capture mode or output compare mode. So when we specify the timer 1 channel 4, this can be used for input or out, and we'll be using these channels for receiving PWM and measuring their widths and periods. We can also use it for receiving other inputs for timing. You'll notice there's only a 1 and a 2 here, so we may have to go to another register to find the 4 and the 3. Here we go. Okay, so it's the CCMR2 that we need to use for the 4th channel. And for this experiment, we're going to set the mode, which is the OC4M. This specifies the mode for this particular pin, and it has 3 bits, 0 to 2, 0, 1, and 2. And we're going to set it to 110. And it doesn't give you any information on this particular part because this is showing the 4th channel. And if you want to know more about these modes, you have to actually go to the 1st channel because you can see that the output compare 1 mode, M mode, and you'll see that 110 is for the PWM mode. And all we have to do is replace all these channel 1s with channel 4. So PWM mode 1 in upcounting, channel 4 is active as long as the timer count is less than the CCR1 value. And remember that the CCR1 value is the duty cycle and the count is just the timer counting. So the channel 4 is active as long as the count is less than the duty cycle, else it is inactive. And since we're not using down counting, we don't have to worry about this portion of it. And really, these two modes are the same except for the down counting mode. So we could probably use this, but I'm going to stick with this particular mode, mode 1. Now that we know this, let's take a look at the program that we had before. In the PSC, we're going to make this a lot smaller. I'm going to go with 100. We can see what happens with that. And the ARR is the period. So I will use 100 as a period as well. So it's an easy number to understand percentages with the duty cycle. So let's put in the duty cycle number, and that's under the CCR register. Let's make it a 50% duty cycle or 50 counts. This isn't actually 50%. If I wanted 50% of, let's say, 200 period, that would have to be 100. So I don't want to confuse you and think that this is actually a percentage. It is, if it's 50%, it would be half of the ARR value. So 25% would be 50 over here. So let's go ahead and keep this at 200 and let's make this one 100. So we get a 50% duty cycle. So let's put in the 110 for the PWM mode. This 0 is at the 0-bit location, and this is at the 1 and the 2-bit location. So it's the OC1M. Let's go ahead and put that in. CCMR2, that's where the 4th channel is located. And we're going to OR equals because we're dealing with bits here. Let's see what it would be called. The OC1M. Oh, I gotta use CCMR2, OC4M. And we want the 1 and the 2. Before I forget, we need to enable the GPIO. So let's do that over here. First, we need to use the reset clock control register and the advanced high control bus. Let's see. Yeah. So we're going to be enabling the A GPIO port because the pin that we're looking for, the channel 4 pin, is PA11, so it's under the GPIO A. And now we have to find its alternate function mode. So this is it here. It's 10 under the mode register. So all we need to do is turn on the number 1 bit and turn off the number 0 bit. Let's go ahead and do that. So first we're going to turn off the 0 bit. We're going to use the AND bitwise operation and the NOT bitwise operation, which is the tilde. We want it to be 0. Number 11. Let's find number 11, and that's 0, the 0 place. We'll do it again for the ones. Okay, so we've set the GPIO PA11 as the alternate function. The next thing is to select the actual pin, or the way it's going to be outputting the PWM. And it states in the datasheet that you must enable the corresponding preload register by setting the output compare for PE. And we can see that the output compare for PE is preload enable. So looking at that particular bit, you can see that if we put a 1 here, preload register on timer 1, which we're using timer 1, CCR1 enabled. Read-write operations access the preload register. The value in the CCR1 is loaded in the active register at each update event. So what I see is the main difference between not using the preload register and using the preload register bit is that when you have a preload register, it is updated at the update event. But if you don't use that, this can be updated immediately and can be written anytime. So let's go ahead and add that to our code. Actually, I think it's in the same register. CCMR2. Yeah, they're there. So I can just simply add it to the end here. Need that other one. One really interesting aspect of this PWM is you have incredible control, and you can actually output a particular polarity if you want it to be active high or active low, which means that when you start out with a PWM signal, you can have it start out high, and you have the duty cycle high, and then it goes low to end the period for the PWM. Or you can have it start out low and then climb up to the start of the duty cycle and then go across to the period and then go back down. So we can output the polarity using the CC4P bit. So let's take a look at the CC1P description. So if we keep it at 0, which is probably at the reset, it'll be active high. If we wanted to start as a low signal and then go up to its duty cycle portion of the pulse, you'd want to set the 1 on that pin. Since that's already on the way I want it, it's reset for that particular pin, I want it to be a active high. So I'm going to keep this at its reset value. And the other thing we need to do is the CC4E, which is the output enabled. We want to make sure that's self-explanatory. We want to make sure it enables the output on that pin. Let's see what the description says anyway. So we can see that 1 being the on state, we want to turn it on. The OC1 signal is output, which is the OC4 signal, is output on the corresponding output pin depending on the MOE, OSSI, OSSR, OIS1, OIS1N, and CC1NE bits. We will be discussing the MOE in a little bit. So this is a dependent aspect for this particular pin. So let's go ahead and turn on the CC4E in this register, the CCER register. Looking for the CC4E. Here we go. Okay, now we've set that to output. Okay, so now we need to enable the MOE, which is the main output enable. By setting 1 in that bit, the output compare outputs are enabled if the respective enabled bits are set. The CC4E, which is what we just set, the CC4NE in the timer 1 CCER register. The break and dead time register description is kind of misleading, but I guess they needed a place to stick this, so this is where it is. So we'll put it right below here. We want to enable the MOE. Here we go. I think the last thing we have to do is set the UG bit in the EGR register. And this is initializing all of the registers before we start using the preload registers. And I wouldn't be too concerned why we're using the UG bit in the EGR register. Just know that this is sort of a requirement that's needed for this function to work. The UG bit we're enabling here. I'm not sure if I really need to show anything on the LCD, but we need to set the alternate function. And we're first going to need to go to the main data sheet for that particular microcontroller, find alternate functions. So we're looking for registers, or for the port A. So we'll look at the port A and we have PA11. Let me see what I have on see if it's correct on the alternate functions. So I have PA11. So I have USART1 CTS and then time 1 channel 4. Let's see, looks like the AF0 is event out and then the USART1 CTS and then time 1 CH4. So you want to go to this sheet to determine which alternate function you need. And this specific one is AF2. And then you can go back to the reference manual and check to see what code you need for the AF2. And you'll see that there are 2 registers. There's an AFRL, which is the alternate function low register, and the AFRH, which is the alternate function high register. And these are the pin assignments. It's 0 through 7 for the low register, and it's 8 through 15 on the high register. So there's 16 pins for each port, and we're using pin number 11. So we're going to have to select this AFR11. But it's not going to be as easy as doing that. The AFRH is actually written as AFR open bracket 1 close bracket in programming. So let's check that out and see what we have to put in. I'm disabling the LCD just to make sure this is going to work correctly. So I disabled the initialize, setup display, and all the LCD stuff that we have in the program. So let's take a look at using the alternate function, GPIOA, and we need the AFR. And you'll see that a bracket showing an array, the size of the array is 2, which is 0 and 1. So we'll go ahead and select that, and then we're going to use the 1, which is the high. We have a couple of options in this. We can use the, just using a binary number, and let's go back to the data sheet to see how many zeros we need. So we would need 0, 0, 4 zeros, 4 zeros, 4 zeros, and for AF2 it's 1, 0. So we need a 1 here. So it's going to be 1 with 13 zeros. So 1 and then 13 zeros. Or we can do it this way. You have a couple of options. Actually, the data sheet shows in its programming examples doing it in this way. Let me see if I can find that. So in this case, they're looking at the low because they're looking at pin number 5. In this case, they're looking at the high and they're going to pin number 9. But because it starts at 0, they have to subtract it by the number of pins that would be in the low. Since this is a little bit more confusing, it's easier just to look at the data sheet on this section here where you're wanting to shift it to the left and you're shifting it 1, 2, 3 times 4. So you have 4 positions on each one. So you're multiplying for each pin 4 times. So let's take a look at how to do that. I'm going to use the equal here. And we can use the 0B10, or we can use 0x02. And we're going to left shift that number, the 02, which is 10. Again, that is 10. In binary, it would be 10. In hex, this would be the number 2. And we're shifting it 3 times 4, which is also 12. So we're shifting 02, 12. And it puts a number 2 at that location. I'm going to keep the binary just to make it a little bit simpler and easier to read. And I'm not using the correct duty cycle register, the CCR register. by me saying number 1, I'm actually specifying channel 1, and I don't want to do that. I want to use channel 4. So we're putting that duty cycle, this number on the channel 4. And if you don't do this, it's not going to work at all. So let's go ahead and see if this program works. To determine if I'm actually getting a PWM signal, I'm putting a multimeter to pin number 44, which is the PA11, and I'm also putting the negative pole or the ground to the negative rail. So we should be able to get a PWM voltage as per the duty cycle that we specify in the program. So if we have a duty cycle of 50%, we should have a voltage coming out of here approximately at about 3 or 1.5 or thereabouts volts. You'll also notice that I changed my ARR value and my CCR values. I used to have it on 200 and 100, but I noticed that I needed a little bit more granularity to get the voltage that I desire. I also changed the prescaler to 0 because I wanted the fastest possible timing here. So the prescaler is at 0 and it's just going at the microcontroller clock speed. So let's take a look at the multimeter output. This is a voltage that I got from using the two values of 2000 to 2000. So let's go ahead and change it to 1000 and let's see if we get a half duty cycle. Should be around 1.5 volts. Okay, so 1.6 volts. That looks right because you saw the other voltage was 3.2, so half of that would be 1.6. So let's try a 25% duty cycle. We got 0.8. That looks really good. So let's see if we increase the ARR value to, let's say, 20,000. Make it a lot larger, and let's make this one 5,000. So to get a 25% of 20,000, let's see if the number changes to see if more resolution will give us a more accurate number. It didn't change that much. It was 0.803, I think. Now it's 0.805. So it might have increased a little bit. Let's look at the full 100% and see if that is actually a little bit higher than the previous 3.2 value. No, it's about the same. So I think in this particular case, I'm going to keep it at pretty low value, relatively low. But these values are going to change for your application, so just keep that in mind. So that is a not so brief look at PWM. This is the edge condition. I plan on using the analog to digital converter from time to time, and I also want to add code to it as well from time to time. So I want to make a header file like I did with the LCD functions and make it so we can quickly initialize the ADC and then start grabbing data from whatever channel that we desire. So let's create a new header file and make some convenient functions for us to use. For now, I'm going to actually eliminate the temperature portion of it because I don't see me using the temperature within the microcontroller for any application, but it's available on video, so you can use it whenever you want to. So I'm going to actually take out any reference to those parts. So let's create a header file. Let's see, make a new file, and we'll call it adc.h. Actually, I don't want to put the .h there. I'm going to use it. Select it this way, and then we'll save it. I think it saved it under timers workspace. Let me see. Let's just go new file. Yeah, look at that. I don't want it under the timers and counters. I want it under, I'm going to do this the manual way, or I could actually delete it. Let me do that. I'm going to delete it here. It's a little bit easier. Okay. And I'm going to go to new file, and I'm going to change the workspace to ADC tutorial. So I'll know that that's going to be the main place for the header file. I'll go to the app because that's where all the files are. .h and ADC. Save. All right, we want to do the same thing that we did in the LCD functions, where we create we pretty much state that this is the LCD functions header, this is the ADC header. So I'm just going to copy and paste that. We don't need the stdio on the ADC, so we're going to release or remove that. And I think it's end if. Yeah, end if. Okay, so all of the code that I want to put in here, it's going to be called ADC functions header, ADC. All the code will reside between the define and the end if. And the next time it tries to open up this header file, if it's already been defined, it won't run any of this again. All right, so let's start copying stuff in here. We'll start with a calibration. I could probably take all of it and do it one time, but I think it's just a little bit easier to do it one at a time, just to make sure that I might want to put them into separate functions. I might not. So let's see. I'm going to start out with, I'm going to peek over at the LCD functions just to see what I'm doing here. I don't think I need to return anything. I'll call this ADC initialize, and I'm not passing anything in, I don't think yet. So we're calibrating. I'm going to put everything in the initialize, and then if I need to separate it out, I can just take something out and make like ADC calibration or whatever. So it looks like we are pretty good here. We're doing just making sure that it's calibrated. So let's keep that the way it is. All right. I'm going to go ahead and put in ADC initialize. Well, we have to include it first. There we go. And I'm going to put in ADC initialize. So we're initializing. We know that the calibration is already in here. So if I ran it from this point, it would probably work. So let's go ahead and take in the clock, selecting the clock, paste it in here. I'm cutting and pasting. So select the clock source. Let's see if there's anything in here that we need to modify or make as a selection for an input parameter. And it doesn't look like it. So I'm going to save that. Now the ADC enable, cut, paste. All right. So we are just enabling it here, and we're making sure that it's ready. All right, that seems to be pretty easy. Now this one is different. This may change the sample rates and the channel select. So this is very important here. So we might want to put that into a separate function. Okay, so let's go ahead and I think I might want to put the sample rates and the channel select in the same function. So let's go ahead and cut this. And I don't think I'm going to be outputting anything from here, so it can be void. And let's see, ADC channel select and sample rates. Maybe I want to separate those two out, but let's do this first. And I'm not sure what I need to input as the channel select yet. So let's take a look. Well, let me go ahead and put the code in here. Channel select is going to be just a simple number, obviously. And we can see that it's an unsigned integer of 32 bits. So we can go ahead and just put that in here. UINT 32, UINT 32T. And we'll call that channel. And then all we would have to do is put in this. So let's go ahead and, you know what, I want to do this first. I want to copy this because make it a little bit smoother for me and less error prone. I'm going to actually put in the channel that I have here. I'm going to cut it because I don't want that in there anymore. I'm going to paste it here, end it with a semicolon. So I'm just going to replace this with channel. On second thought, I would like to just say channel 1 or channel 2 or channel 3. So let's look at the differences between the channels and see what main differences these are. So let's make a few of these. Channel 2, channel 3. I don't know how many channels there are actually. Let me see. Let me do this here. Here we go. So it looks like we have 18. Channel select. Here we go. Looks like we have 18 of them. And we know one of them is voltage and one of them is temperature. But we'll go ahead and allow it for the 18. So we'll start with 0. That's going to be, no, it's not going to be syntax here. So that's good. I'm doing it this way because I want to look at an alternative way to going to the data sheet. We don't really need to go to the data sheet if we have these variables or defines macros here. So you can see it's upping it by 1. So you got 1, 2, 4, which is the bit next to it, 8, 10. So all we're doing is we're shifting the bit 20, 40, and 80. So all we're doing is we're moving the bit over 1. So that's pretty simple to do. And this is just using the left shift. So if we take a look at the hexadecimal number 1 and 2, 4, 8, let's go ahead and do a conversion from hex to binary, and you'll see how the 1 is shifted from one to the next. So 0x1 should be in the 1's place, and then if you do 2, it's in the next place. You can see how it moves. 4, which was the next one, it's just moving to the left. 8, there you go. So all we're doing is with a particular channel, this would be channel 0, this would be channel 1, this would be channel 2, channel 3, and all we're doing is we're doing a left shift operation. So that's pretty easy to do, obviously, we know that. So in the channels, for the channel select, let's just go ahead and put in very simple UINT. Is there an 8 here? Let's see. Okay, so there was a fast 8. I'll try it out. What the heck? Okay, so, well, if we put in channel 0, then we should expect channel 0. So we'll make that the UINT fast 8, whatever that is. I've never heard of that. But we're going to put the channel in there, and this is going to change because we want the 1, we want to left shift channel. But when channel is 0, we have to say channel plus 1. Actually, no, we want to keep it 0 because we want it in the 0th place. So let's keep it that way. To keep this video simple and to ease your way into ADC and the more complexities of ADC, I'm going to keep the sample rate the way it is. I believe I'm using the slowest sample rate. So I'm going to put this into the initialization area because we're probably not going to be changing this very often. And we'll only when we really want the microcontroller to work in an extremely efficient manner. We don't really need to work with it right now. And the sample rate is going to be determined by a lot of different factors anyway. And that would be circuit factors, not necessarily programming factors. And having the knowledge of the circuitry of the ADC that's going into the ADC pin, resistance and things like that, these sample rates may be able to change. But let's keep this simple and we can scaffold the way into the future. So let's keep it this way first. So this one really is the only thing we're going to be messing with is the sample, is the channel select. Let's see. Let's make channel select. And you know, this UINT fast 8T might actually, I'm not sure if I should keep it or not. If I just use a standard int, it might actually make it a little easier to know what to put in when you're actually putting in the function or using the function. So let's see what it says when I try to put something in here. Yeah, you can see it says UINT fast 8 channel, and that gets a little bit confusing. And then you can see that it's expecting some variable or some number of UINT fast 8T, which I don't think I've ever used myself. And it'll be interesting to see what happens when I use it. I'm going to keep it the way it is, but I might change it later on to just int or something a little bit more understandable when you're trying to put in a number here. All right, let's see if this still compiles or builds. Okay, good. All right, so this is kind of bugging me a little bit, so I'm going to take that out. Channel select is 0. We have initialize and we have channel select. You can see that I'm using the same components, using the potentiometer to provide a voltage onto the pin number 15. So everything should be the same as before. So I'm going to plug it in. I'm going to flash the microcontroller. All right, looks like we have something on the display. See if we can get a better shot of this. Okay, that's better. Okay, so we have a potentiometer, and it doesn't look like it's changing. I wonder which channel I actually used. Did I use channel 0? Let's try channel 1. I think I used channel 1. Yeah, let's do another build and flash. All right. Looks like it's a little more stable. Let's see. Yeah, okay, that's the one. I'm turning the potentiometer, so we are getting a change of numbers there. Okay, so now we have the ADC in a very convenient little package up here in a .h file. So we don't really need to see that code anymore. All we need to do is initialize it, select the channel, and then read what the contents is on the ADC. I want to try a couple experiments. The first one is I want to just go ahead and plug in the PWM signal coming out of the PWM pin, I think it was PA11, and stick it right into the ADC channel 1 pin and see what measurements we can get from the ADC. So let's try that. First, I need to get the ADC.h into this project. So we have it available here, and we want to add it to the include ADC.h. You can see it's available, and I'm going to go ahead and make the LCD work as well. I think we have no conflictions, but we'll find out. I do want to change what's being sent to the LCD, obviously, because I'm not going to be considering the counter and prescaler. I'm going to be considering the ADC. So let's just say ADC output, and I'll put nothing on the next line. So the ADC output, this would be 0, 1, 2, 3, and then 4 and 5. So I'll put it on the 5th location. And this one will be, we're not going to put anything here. But over here, we want to put in the ADC. I think it was the DR. I think it was ADC1. Yeah, the DR. Okay, so we got that right. And it's going to be 5, position number 5 on the first line. All right, so we're going to connect pin number 44, PA11. We're going to connect that to pin number 15, is PA1, which is channel number 1. So the potentiometer from the previous project was removed, and the wire going from pin 44 to pin 15. This is the ADC input. This is the PWM output. Let's see what the ADC shows from a PWM output. But we also have to add the ADC initialization in here. We haven't done that yet. So let's go ahead and initialize the ADC. And we're going to select the channel select, and we're going to select channel 1. Okay, so we've selected ADC channel 1. Okay, I'm back over here at the ADC project that we were doing before. Copy this portion into the other program. So let's go ahead and put that in here. Okay, so now we're starting the ADC process and checking to make sure we're okay. You can see that the readout, if you look at the, it's going from 0 to 4068, pretty much at the top end of the voltage. It's doing exactly what it's supposed to be doing. It is taking in a PWM signal, and PWM is a square wave, and the ADC is actually working a little bit too fast to take in a voltage from a PWM signal. It is actually taking in the square wave, and that's not what we want, obviously. And the only way to be able to get a voltage out of a PWM is actually to add an RC circuit, a resistor capacitor circuit, to smooth it out to a nice smooth voltage. Without an oscilloscope and a little bit of research on what capacitor and resistor I would need to smooth out this, let's go ahead and do the reverse. I'm going to hook up the potentiometer again and take the ADC number that we have, the digital number, and we're going to plug it into the PWM so we can cause the output voltage on the PWM to be variable according to the potentiometer setting. So let's go ahead and add the potentiometer back to the ADC pin here. This is pin number 15. So it looks like the ADC still works with the potentiometer. So I'm turning the potentiometer and we get a pretty good readout. So I also want to connect the multimeter to the PWM output so we can see what the output will be when we change the PWM duty cycle according to the analog to digital converter. So I still have the PWM connected to the 44 pin. And I'm going to take my multimeter and just connect the positive lead to that pin. And I'll connect the negative lead. This is the positive lead going to that pin. And then the negative lead, I'm going to put to the negative rail. So I have the duty cycle at 50%. And on the multimeter, it shows 1.5, which makes sense. So let's change the PWM duty cycle, and just to make sure everything is working correctly. So we'll make it 2000, and we'll make this one 500 to get a 25% duty cycle flash. And it should be around 0.8. There we go. Good. So now let's take the analog to digital conversion, the ADC1 DR, and let's plug this number into the CCR4. But we also have to understand that we have to look at the duty cycle limits from the ADC, because the ADC is a 12-bit number. So if we go back to binary to decimal converter, let's see what a 12-bit number would be in decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's 4095. So that makes sense. So let's go in here and make the period 4095, because that would be a 100%. If the CCR4 value was 4095, that would be a 100%. So we want to take the CCR value. Let's keep one here just to sort of initialize it. We'll make it 50%. So that's around 2000. And let's take another CCR and bring it in here. And I'm going to, actually I want to put it above the time delay, actually in the first part of it. No, I want to make sure that I have the ADC DR available to me when I'm using it. So I'm going to take the ADC DR, I'm I'm going to copy it and put it right into the CCR4, which is the duty cycle number. And we'll see if we can change the PWM, the voltage coming out of that, by modifying the potentiometer. Let's check it out. Let's see if I can get everything in frame here. So we know what the ADC signal is. So we can see that the ADC is about 2480. Let's turn the ADC. We'll turn the potentiometer. Let's go up. It looks like we're affecting the voltage. So we are changing the PWM signal by turning the potentiometer. And I'm turning it down now. So we're almost at ADC 400, 300. We're almost to the zero. I don't want to go all the way to zero. So you can see we got 0.142 volts. So let's turn it up again. You can see that we are getting, I want to go up all the way. So we got 3.1. Okay, so I turned it down. So it looks like we were successful in one portion of this video where we're affecting the PWM signal coming out. And you can just imagine the applications we could do with this by, say, having a servo connected to the PWM signal coming out, and by turning the potentiometer, we can move the servo. So that's one application. I'd like to show you a short demonstration. Since we have a PWM output on pin number 44, showing the voltage from a multimeter really isn't that interesting. So I'm going to add an LED to this pin so you can see the dimming of the LED controlled by the potentiometer from the analog to digital converter. In last video, we used this potentiometer to control the PWM duty cycle, causing the voltage change in a digital way. What we'll do in this experiment is just connect an LED to pin number 44 using 330 ohm resistor and the LED to ground. The PWM will be essentially blinking on and off extremely fast, making the LED look like it's dim, but really it's just switching on and off extremely fast. In the program, the first thing I want to do is take out the time delay for the LCD, because the time delay actually makes it cause flickering with the LED when you're changing the ADC. It doesn't cause any flickering during the PWM because the PWM is constantly being output on that pin, and that is not being affected by anything in the program except for the modification at the CCR4, which is the change of the duty cycle in this case. So let's go ahead and add the resistor and LED to pin number 44. Okay, after building and flashing the microcontroller, we can control the LED's brightness by turning the potentiometer. You can also use a more automatic approach if you wanted to have an LED dim up in brightness, smoothly get brighter, and then dimmer and brighter and dimmer. You can do that with the duty cycle and the PWM as well. One of the examples that I like to use to demonstrate PWM, pulse width modulation, is on how to control a hobby servo. And this is specific to analog servos. Since there are digital servos and analog servos, digital servos only require a specific communications protocol where you're just sending information via some protocol like I2C. But with analog servos, they require PWM signal at a 20 millisecond period. So what is a 20 millisecond period? You can think of this as a portion of a 1 second period. So let's draw a 1 second period. A 1 second period has 1000 milliseconds. So if this line represents 1 second, this would have 1000 milliseconds along this line. So 20 milliseconds would be represented by each tick represents 40 milliseconds. Because if we take 1000 milliseconds and divide it by 20 milliseconds, we would have 50 parts. And in this 1 second, we have 50 spaces between the ticks. So the servo is going to require us to create PWM signal with a pulse between each one of those ticks. The pulse is actually going to be relatively narrow, and the width of this pulse here will represent the rotation of the horn on the servo. And we learned from the other tutorials that the ARR determines the period, and the CCR, and the number after the CCR is the specific channel we're using for the timer, determines the duty cycle. And the duty cycle in this case will determine the rotation of the servo's arm, the servo's horn. So our first task that we need to do is we need to determine the period. Okay, so first we need to start somewhere to figure out this ARR value. The data sheet of the microcontroller that I'm using states that the clock speed at reset is 8 megahertz. So what does that mean? This second here, from this point to this point, is 8 million cycles. And we know that we have 50 partitions. So 8 million divided by 50 partitions, because we need to figure out how many cycles is in a single period here. And this equals 160,000. Well, this value is actually too high for an ARR value. The ARR value can only go up to 65,535. So this is where the prescaler comes into play. If we use a prescaler of 1, that would essentially divide this 8 million by 2. So let's just, for the sake of argument, divide this by 2. That would be 4 million. Divided by 50, that would be 80,000. That's the same thing as taking the 160,000 and dividing that by 2. So if we have a prescaler of 1, we're dividing this by 2. If we have a prescaler of 2, it's dividing this by 3. So let's see what that would be. Okay, that's 53,333.33 repeating. I'm not sure if I like a number that has a decimal in it. So let's use a prescaler of 4 and see what that gives us. And that would be 40,000. So that works. So if we kept the prescaler at 4, that's the PSC number, we would use the 40,000 for our ARR number. But we're just assuming that the microcontroller is 8 megahertz. We're just hoping that the data sheet is correct. So let's go ahead and do some tests to make sure that 40,000 done 50 times would equal 1 second. So we could actually have a routine in the microcontroller in our programming, and we can have the microcontroller only when this is counted up 50 times. It would maybe show a count up on an LCD, and we can determine our sort of human sense of what a second is and see if it does look like a second. And that would verify that the 8 million or 8 megahertz is an actual correct number that our microcontroller is set. Let's make a library from our PWM code so we don't have to keep rewriting all of this stuff. In the beginning, we'll just make a simple library. So we'll first a new file. I guess we can call it PWM functions. And we'll use the .h header file, and let's go ahead and save. So now we have PWM functions. We have our blank screen here. So let's go ahead and take a look at the LCD functions and see how I did the if not defined. So I'll just copy that in. I don't need this stdio. I'll just take that out, and then I'll end if. So anything that happens inside of here will be executed once. So let's take all of our stuff that relates to the timer and the PWM, and we're gonna copy it or cut it and then paste it here. Let's wrap a temporary function around it. Void PWM function. Doesn't really matter what I'm going to put in here yet. And then I'll just put everything in here. Okay, at this point, I don't want to make it any more complicated than what it is. But I'm going to change this to setup, I think. PWM setup, and I want to try to keep everything in this order. So that's one of the reasons why I don't want to do anything more complicated, because I could have in like maybe an input for a timer number and timer channel, but I want to just maintain the order and the way it is now. So I'm going to put PWM setup channel 4. We can add more later. I know I need to change these numbers here, the prescaler, period, and the duty cycle. So let's go ahead and put those in first. We're going to make them regular integers because they actually have a pretty high number. They can go up to 65,535. So the prescaler, we'll just call it prescaler. And we'll have an input for period and an input for the duty cycle. All we'll do is just come in here and place these, period, and the duty cycle. Okay, so I think we can go ahead and start using this now. So let's just go ahead and I'm going to copy it and paste this. And then PWM functions, header. And the PWM and timer setup stuff was over here. So let's go ahead and put it right here. Take out the void because we don't need that anymore. And let's create a prescaler. And we're going to use prescaler of 4. So we'll put 3 there because it's 0, 1, 2, and 3, which makes 4 counts in the prescaler. In the period, we wanted 40,000. So let's go with 39,999. So that should be 40,000 with a 0 index. And the duty cycle, we don't know that yet actually. So let's just put in 2,000. It's not really necessary right now to put in the correct number because we're just going to see if we got the timing right. Put a semicolon at the end. Let's keep the ADC stuff with the LCD, and I'm just going to put in count on the next line for the LCD so we can see how it's counting up. Let's remove this because we don't need this anymore. I think I'm going to remove this here. What this part of the code is doing is we're putting in the ADC into the duty cycle to change the duty cycle, but we're not going to do that right now. And we don't need to look at, well, we can look where the ADC is showing. It doesn't really affect that. What we're about to do, so what we want to do is show the count of the timer. Put on the second line here, 1, and see where on that line, 8. Actually, I think it's 7 because it started from 1, not 0. So I'm going to include this at the end. PWM functions. Well, now that we've changed the PWM, or we've set it up to output a PWM the way we want it to, this is probably not what we're going to need to look and see if we have the proper timing using the 40,000 as the period, because we need to see what the timer, we want to just confirm that 40,000 is the right number, but we need to actually be able to see it with our own eyes and look at it in the LCD. And the only way we're going to do that is to actually put the 40,000 in the prescaler. And the ARR value, because we have a prescaler of 4, when it gets up to 200, because if we're looking at multiples of 50. So when it goes up to 50, we know that we've covered 1 second if there was a prescaler of 4. But since we can't do 4 times this number, and it would go above the capacity of that type, of that data type, we're going to have to put 200 here, because that's 50 times 4 would be 200. So for every 200 counts up using the ARR, that would be 1 second. Let me put this down to like 10 or something like that. We don't want to cause any problems with the duty cycle being any more than the period. So the ARR number is what's going to be resetting the counter. It's going to be counting up to 200, and then it's going to go reset it back down to 0. So when we take a look at this, we could actually see it counting up to 0 or up to 200 and then down to 0 every single second. Let's go ahead and see what that looks like. Okay, we flashed the microcontroller. You can see it's counting from 0 to 200 every second. So if I just count like I would normally do for each second. So if we count normally like 1, 2, 3, 4, 5, we can see that it's counting for every second. But that doesn't give us enough clarity and understanding whether it's doing it right or not. So let's see if we can have it actually count seconds, just to make sure that we're confirming that our 8 megahertz is really 8 megahertz. We're not going to be able to go in here and just do a conditional statement with the count, because we're not going to be able to capture a specific count, because this program is working a lot slower than the counter is working. So if I said like, if timer counter equals 200, then increment a second, we would miss that 200 some of the times. So the only way to actually look at incrementing for each second, we're going to have to look at interrupt. And there is an interrupt flag that we can access for this timer, and it's called the UIF, Update Interrupt Flag. And the way it works is, if you look at one of these diagrams, you can see it counting up. When the counter is reset at 0, the Update Interrupt flag is set. And once it's set up high, I can count 1 second, and then I can reset it by software. I can actually put a 0 in this flag. So let's go ahead and do that and see what that would take. So I know I have to look at this register, or this in the register. It's in the SR register, I believe. And I also need to make sure that the URS bit is set as well. So let's take a look and find out where that URS bit is located. The URS bit is located in the control register for the timer 1. See it right here at the second bit place. And see if we can find out more about it. The update request source. This bit is set and cleared by software to select the UEV event sources. And I believe it really doesn't matter, because we're looking for the underflow or overflow. So it looks like it'll work with either 0 or 1. If I wanted to get the UIF to be high on the UG bit, then I would want 0, or for the slave mode controller. But that's not really important to me. I'm really concerned with the counter overflow and underflow. So let's see if this works. So I shouldn't have to update this at all. So let's go ahead and just look at the UIF flag and see what happens. So if the time 1 SR the status register, and there we go, the SRUIF. Then, so this is where we want to increment the second, and then we're going to set it back to, we're going to reset it. So let's create a new variable called seconds counter. We'll make it 0, and we will increment that whenever this flag is invoked. And now I'm going to reset the flag. Okay, and we still need to display it on the LCD, so let's go ahead and do that. So instead of doing this, showing the timer counter, we'll show the seconds. So this should show us seconds. Let's see if this works. And we have no errors. Flash the microcontroller and see what happens. Okay, it looks like we have correct output. It looks like it's going up 1 second. So we have just confirmed that we have an 8 megahertz microcontroller. It's set at 8 megahertz, and that is what it says in the data sheet. And it is counting up 1 second at a time. So we know that putting in the PWM the way we want to for the servo would work fine. So 40,000 is the correct number. So let's determine what the duty cycle needs to be. So let's take a look at the data sheet for the servo that I'm going to be using. So I've got a high-tech HS322HD. So let's see if we can find some information on that. Okay, so I found the specifications for the PWM pulse data for the high-tech servos, and this is for all their analog servos. And the duty cycle needs to be between 0.9 milliseconds to 2.1 milliseconds, with 1.5, which is right in the middle of the 0.9 and 2.1 as the center. And the pulse refreshes every 20 milliseconds. We've already established this. So now we need to create the duty cycle between 0.9 and 2.1 milliseconds. So if 40,000 represents 20 milliseconds, 1 millisecond should be 40,000 divided by 20. So let's see what that is. So the low end of the duty cycle is 0.9 milliseconds. And with our 2,000 counts per millisecond, that would be 0.9 times 2,000, which is equal to 1,800 milliseconds, or 1,800 counts. That would equal the low end duty cycle. I'll put this on another line here. And 2.1 milliseconds is equal to 2.1 times 2,000, which is equal to 4,200. So you can see that our low end is 1,800. That is the horn at one position, and 4,200 is this would be the minimum position, and this would be the maximum position. And I think this would be maybe, let's say, 0 degrees and 180 degrees. So let's go ahead and set up this. I think what we need to do first, we need to work on this library just a little bit more, because I think we're going to have to separate out something to make it work, because I don't want this to be repeated all the time when I'm making a change to the prescaler, period, and duty cycle. I don't want to have to keep putting this code in or running that code. So I'm going to create another one called void PWM channel 4 set period and duty cycle, or set parameters. I'm going to say set parameters. That's a little bit easier. And then I'm going to take the parameters in here. I still want this to stay because when I'm initializing it, so we can take this prescaler, period, and duty cycle and just copy it to this one. And so what we're doing is we're going to replace this portion here with this. So we're not repeating the code at least. So whatever we have set here, we're going to pass it into this function. And we can also have this function available to us to set parameters in the main. So let's go ahead and do that. But we don't need to do this anymore. We can take this out. All right. So let's go ahead and put in the PWM channel for set parameters. And I'm going to put in the same things that I have here. Actually, I need to change this to at least like 1800. So let's do that. Okay, so now I have it at this location, and then I want to change it to 4200 so it swings in the other direction. But it's going to do this so fast that the servo is not even going to move, or it may jitter because it's trying to change the location too quickly. So we need to put a time delay right here. So let's make it 100,000. That may not be enough. Let's go ahead and put 100,000 between them. So we should have the servo turning from 0 degrees to 180 degrees and back. So it's just going to go back and forth. Let's see if that works. First, we need to connect the servo. So we'll need a 5-volt connection at the red. We'll need a ground at the black. And at the yellow, we can have our PWM. I don't think the yellow needs to have 5 volts as its pulse. I believe I remember seeing in the data sheet that it can be 3 volts. I think it was like 3 to 5 volts. So let's go ahead and try that. We'll put the signal in on the PWM here, 5 volts in the middle pin and ground on the end. Before I actually connect the servo, I want to build and flash this microcontroller first, just so it can be in the right state, so I don't cause the servo to go to any extremes. And it looks like I have okay, I'm not even using my variable, unused variable. I'll just take it out just for the fun. Something else. Okay, I see the problem here. I put this function after I actually am using it. So it needs to be before this, or I need to create a prototype. I like to do. All right, this is like sort of a programming thing. I'm sure there are opinions both ways on this. All right, so let's go ahead and try to pilot again. Good, it worked. I'm going to go ahead and flash it. Okay, so the microcontroller is flashed. Let's go ahead and connect the servo. Okay, just plugged it in, and you can see that it's going a little bit too fast for the servo to handle the instructions, going all the way back and forth. So let's increase the time delays and see if that helps. Okay, we can see that we have successfully been able to connect the servo to the PWM. We were able to modify its position by using the PWM. The one thing I did have to do is I had to change the location of my 5 volts because I was causing the LCD to reset every time the servo was changing its position. Rather than applying the 5 volts from my ST-Link, this is the 5 volts here, I've elected to use a battery pack instead because I don't want any interference or back EMF from the servo affecting my circuit. So in this type of situation, you want to have the battery pack plugged into the red lead, and you also want the black lead from the battery pack, which is the ground, to be plugged into the black lead. But you also want the ground from the circuit to be plugged in to the servo ground lead. I'm actually having a difficult time getting both of these wires into this small connector, so it's just as good to put the ground from the battery pack into a ground on the circuit. And then you can take the pin from the PWM and put that into the yellow lead of the servo. And that way you'll have a voltage source that's external from the circuit, and the servo will not interfere with the circuit in any way. And as you can see, with the external battery pack and the flashed microcontroller, we have a functioning circuit, and the external voltage source is actually what's recommended from the manufacturer of the servo. They recommend using battery cells to... I'm going to use a potentiometer to control a servo, where when you turn the potentiometer, the servo horn will also turn in synchrony. The potentiometer is connected to the ADC, the analog digital converter. The number that is captured from the analog to digital converter is fed into a PWM signal to modify the duty cycle that will control the servo's horn. We first need to include the STM32F0XX.H file, and that will contain all the registers that we need to control the features of the microcontroller. Next, we need to include the LCD functions. Next, we can include the ADC.H file. And finally, we can include the PWM function. In the main function, we're going to add some initialization functions from the LCD and setting up the LCD display, the ADC, and we want to select the channel for the ADC, which is specifying a specific pin that is going to be receiving the analog signal. And the PWM has to be set up with the proper prescaler, PWM duty cycle, and the PWM period. In this case, we're using a prescaler of 3 and a period of 40,000. To make sure that we're not going to start off the servo in extreme position, we're going to start off with the duty cycle at 1800, which is the low end for the servo. Let's go ahead and set up the LCD so it can display the number that is converted from the ADC. In this part of the program, we just need to add a label signifying on the LCD what we're going to be showing. I'm going to simply just put ADC on the display and nothing on the second line. Within the while loop, we need to capture the ADC conversion. And to start the conversion, we'll use the control register and the bit called AD start. Right when you invoke the AD start bit, the microcontroller is going to start to go through a process of conversion. So we want to look at a particular bit that will be set by the hardware that is called the end of conversion. So let's put in a while loop that tests for this bit. The conversion has been completed. After this while loop, the conversion is ready. So we can actually use the number that is stored that represents this conversion. Specifically in this case, potentiometer's position. So let's go ahead and display this number on the LCD right after the ADC colon on the display. And that location is 5 on the first line, which is line 0. The converted number is stored in the DR register under the ADC1, and that is called the data register. We can simply just take that number and display it. Since the number will be a maximum of 4095, I'm only using 5 digits. Let's see if our conversion works and the number correctly displays on the LCD. You can build the program and then flash the microcontroller. It looks like there's an error, and it looks like it has to do with the LCD send an integer function. It looks like I used a parentheses around the actual parameters, which makes it look like there's only a single parameter. So removing these parentheses will hopefully fix the error. Let's try building it again and see if it works. There's no errors, so we can go ahead and flash the microcontroller. The microcontroller was flashed. Let's see if it works. The ADC number seems to be changing when I turn the potentiometer. Let's see if the range works from 0 to 4095. So it looks like it goes all the way up 4095. 4095, and it goes all the way down to 0. Now we want to do a little bit of math to make sure that the ADC number is not going to go outside of the constraints of the PWM duty cycle that the servo will accept. The ADC has a range from 0 to 4095 from one extreme of the potentiometer to the other, and the servo has a range from 1800 to 4200. That comes out to 2400, so our width of our PWM cannot exceed 2400, and it has to start at 1800. So we want to take the 4095 and reduce that range to 2400. So let's determine the coefficient we need to establish this range. So it looks like it comes out to approximately 0.586. So if we multiply 0.586 by 4095, we should get the correct range. Let's go ahead and plug this into our code where we show it on the LCD, so we can determine if this coefficient is correct. Looks like there's no errors in the code, so we can go ahead and flash the microcontroller and test the output. It can immediately be seen that the number is different in the 800s, where it was before it was in the 1300s, I believe. And let's go ahead and go all the way up and down on the potentiometer, and it looks like we have the correct range. It went to 2399 and down to 0. Now we need to add the 1800 to this number. So let's contain the multiplication we just did and then add 1800 to it, so the order of operations is done correctly. This should shift the value on the ADC up 1800, so the range now will be 1800 to 4200. So let's test the range of the potentiometer. Let's see if we get 1800 on the low end. Yep. And 4200 on the high end. There we go. 4199 is close enough. So now let's use the servo as our output device. The new computation number, the ADC multiplied by the 0.586 plus the 1800, can be plugged into the PWM duty cycle portion of the function. This is a sub-function that I created just to modify the prescaler, period, and duty cycle. So let's plug in the 3, the 40,000, and we can copy and paste the number that we are displaying in the LCD, plug it right into the duty cycle input on that function. Even though I don't have the servo connected to the circuit, I want to build and flash the microcontroller anyway, so the circuit will be ready for the servo. To connect the servo to the PWM output, I'm connecting a hookup wire from the signal in of the servo to the PWM out on the microcontroller. Connect the ground of the servo to the ground rail on the breadboard to serve as a common ground. This will provide the ground that the PWM signal will need. The servo will get its power from 4 AA batteries. Positive side will go to the servo, and the negative will go to the common ground. After plugging in the programmer to provide power to the circuit should function correctly. When the potentiometer is turned, the servo should turn with the potentiometer. If the outer potentiometer leads were wired in reverse, one going to VCC and the other going to ground, then you might have the opposite happen. When you turn the potentiometer one way, the servo may turn the other direction. I hope you enjoyed this experiment as much as Snickers did. Interrupts are probably the most important feature of microcontrollers. An interrupt will stop the main code from processing and switch over to a function that is responsible for the interrupt. When the interrupt function completes its task, the main code continues from where it left off. Right. Yeah. Let's pretend that I am the standard program flow, which is the code in the main function, and each word that I speak is a piece of code in the never-ending while loop. My wife here is obviously the interrupt function. Her only responsibility is stopping me from processing or talking, and for her to process a few lines of code. In this scenario, she is responsible for receiving characters on the RX line. For each character that is on the RX line that reaches the RX buffer, the main code, me, will stop and her code will automatically begin. Once she has received the character from the RX buffer, she can store it in a variable, so I, the main code, can use that variable in some way. You need to be really careful with the code that you add to the interrupt function. In the scenario just shown where my wife serves as the interrupt function, the function simply reads the character in the RX buffer
and adds that character into the global variable. The global variable would be something like an array or a pointer that stores all of the received characters, at least the ones that haven't been used so far by the main code. The code that stores the characters can be as little as a single line of code inside of the interrupt function. Remember that the interrupt function only fires if there's a character in the Rx buffer, so you are ready to read that character immediately. You don't want to add a lot of code to the interrupt function. In the interrupt function, you may be tempted to take the character and send it out to a terminal, or worse, add it to an LCD, which is super slow. Here's an example of what could happen if the interrupt function tries to take the character and put it on an LCD. The lines of code to get a character on an LCD is not few. And if you have my book, you would know that because I teach you how to communicate with the LCD. So the time it takes to process that amount of code, and that the LCD requires a lot of wait time to communicate to it, you could miss characters coming in on the Rx line that's coming into the Rx buffer. Instead, let the main code handle the slow stuff. You can be assured that no characters will be missed if you simply add the characters to a global variable that can be accessed by the main code. I talked about polling in previous videos on my channel and in my book, so if you've watched those videos or read that section of the book and tried the projects, you can see how much better interrupts can be. Can you imagine not using an interrupt routine and the main code having to wait for the Rx buffer to be full? The time it takes for a character to be received by the Rx buffer could be a long time if the characters are produced by a human on a computer or a terminal. We would never know when a character would be sent to the microcontroller. This would be a problem with using the polling technique. Your main code can handle a lot of different tasks, and when an interrupt happens for whatever the interrupt calls for, your main code can be swimming along freely doing its thing. But in the polling technique, it's just waiting for that character to be received by the Rx buffer. The types of interrupts you have for microcontrollers spans the breadth of features in the microcontroller. That is to say, if the feature exists in the microcontroller, it probably has an interrupt for it. How do you access these interrupts or make them work? They're called interrupt vectors, which is just saying the location in the microcontroller that you can access the interrupt. It's like an address. With the microcontroller that I'm using in this series, the interrupt types include signals from external pins of the microcontroller exceptions, where you may need to handle an issue that your program is having, your own self-created interrupts, the independent watchdog for program robustness, timer interrupts, including the system timer, real-time clock, and all of the specific timers in your microcontroller. This can even be associated with features like PWM signals, infrared remote sensing, which is actually related to timers, and the many other ways you may want to configure your timers. Communication interrupts, including USART, which is Universal Synchronous Asynchronous Receive and Transmit, SPI, which is Serial Peripheral Interface, I2C or IIC, which is Inter-Integrated Circuits, which we'll be getting into later, and others, if your microcontroller has those communication features, such as CAN, which is Control Area Network, and USB, for example. ADC, Analog to Digital Converter, where the interrupt fires when the microcontroller completes a conversion from an analog signal, say 0 to 3.3 volts, and converts it to a number to, say, 0 to 1023. This is how many sensors will be set up in this series. You can have an interrupt trigger for almost anything you need in your program.
I'm going to be showing ADC conversions, analog to digital converter conversions, from channel 1, which is this potentiometer's location on the microcontroller, and it will be showing its output on the LCD. The difference between this implementation of ADC and the previous one is the previous one did single conversions and it was polling in a loop. In this implementation, I'm going to be using interrupts, so we don't have to continually poll the ADC in the while loop. Instead, the microcontroller is going to know when the conversion is ended, and it can go to another part of the program to show the contents of the ADC, the data register. So let's see how we can do this. Let's go ahead and add the include files. And the first one is going to be the one for our chip, the STM32F0XX.h file. We'll include the LCD file, LCD functions. And the last file that we need is the ADC file. Before I continue, let me explain a little bit about interrupts. You can think of interrupts like an intention grammar for microcontrollers. So far, you've seen me use the while loop. The while loop will run these instructions over and over again, infinitely, while there's power going to the microcontroller. You may actually have many instructions within this while loop, and the while loop will continually run these instructions, and it'll start all the way back over again and continue going. This is probably fine for most circumstances. But with microcontrollers, a lot of these instructions cause the microcontroller to stop until this instruction has cleared some kind of flag. For instance, the ADC EOC, the EOC end of conversion flag, has to be true to continue on to the next instruction. So the microcontroller is actually stuck at this location waiting for the end of conversion flag to be set, and nothing else after this can be run. There could be really important operations happening after the waiting of the end of conversion flag that the microcontroller will never see until that end of conversion flag is finally set. So when programming, it would be good to only add the important operations that need to continually execute within the while loop, the never-ending loop, and let the microcontroller execute the interrupts when it thinks it's ready. The way this works is that when the while loop is running these operations, so let's say it's at this particular operation right now, and then it's about to go to this operation, and then it runs this operation, and then right before it gets to this operation, the EOC flag, or the end of conversion flag for the ADC, is set. So what it does is it goes to the ADC interrupt function and it processes all the ADC code that you need it to run. When you get to this particular point within this interrupt function, you'll already have the number in the data register, and you can use that number however you need within this particular interrupt. But as I mentioned in the AVR series, it's best to keep this portion of the code, the interrupt code, relatively small. So what you can do is you can take this data register information and you can put it into a variable, a non-volatile variable, so you can use it in the main code where you have the important operations. So when this code is complete, it will go right back to where it stopped processing and then continue, and then go all the way back to the beginning again and do all of the operations until it sees the end of conversion happen again. Just to drive this idea home, while in the while loop, it'll execute the important operations and it'll go back to the beginning. And let's say the EOC happened here, end of conversion. It'll go to the ADC interrupt. When it's done, it'll go right back to where it left off. It'll do the next operation. And let's say it happened again here. It'll go back to the interrupt and it'll go back to where it left off, and it'll continue over and over again. Let's say it happened right here. It'll go to the interrupt, come right back to where it left off, and then go back to the beginning and start all over again. So it doesn't matter where in the while loop it happens, where it'll pick up the ADC interrupt. It'll go to the ADC interrupt and then go right back to where it left off in the program. This is one of the coolest things you have with microcontrollers, because you can have some incredibly complex code within the while loop controlling a very sophisticated robot or whatever device that you are creating. And the microcontroller has a separate process that considers interrupts, whether it's a timer interrupt, an ADC interrupt, an external interrupt, or a software interrupt. It can handle that as a separate process and then remember where it was in the never-ending loop and continue exactly where it left off. So let's go back to the code and see how this works. Before we go to the code, let's add the components to the circuit. We'll start with the potentiometer, going to pin number 15. Connect one leg of the potentiometer to the positive rail and the other leg of the potentiometer to the negative rail. Make sure you have the programmer plugged in. You'll be ready to flash when the code is complete. So this is our never-ending loop here. This is where important code is going to be. The microcontroller is going to continually run this while the microcontroller is on. As you know, it first executes whatever is before the while loop. So we're going to be doing our initializations for the LCD and the ADC here. And interestingly, we're not going to actually put any code in here at all, because when you're using interrupts, you can have code in here, but what we're doing is we're only going to be converting the ADC value and executing that within the interrupt function itself. So we can add code into the while loop when we want it to do other tasks. Let's go ahead and put the initialization code in, and we'll put in the ADC initialization code. We won't have to make any changes to this initialization for the ADC. If you look at it, we're doing the calibration, we're setting the clock, which is required for the interrupt, and we're enabling it, and we're creating a specific sample rate. We also have the channel select. So let's go ahead and do that. And we're selecting channel number 1, which is where the potentiometer is located. In the ADC code we did previously, we did it in single conversion mode, which means that we had to start the conversion. That would be AD start, setting the AD start bit. And then we wanted to wait until the EOC, the end of conversion, is set. And this is the kind of thing we don't want to do. We don't want the microcontroller to wait for anything. We want the microcontroller to continually go and do important code in here and not have to wait. We want this to be done in another part of the program. So this is what we did before. And then what we did is we used the contents of the ADC data register. And this would happen over and over again. And that is called polling. We're polling the ADC. So instead of doing single conversion mode, let's go ahead and make it continuous conversion mode. So it'll always do it by itself internally and always convert without us having to poll it. And to do that, we need to access the ADC configuration register and set the CONT bit. And the CONT bit, we didn't set it, so it automatically went to single conversion mode before. So in this case, we want to put it into continuous conversion mode by typing ADC1, accessing the configuration register, and we're going to set the bit for continuous conversion mode. Now we need to enable the interrupt. We have to tell the configuration, the ADC, that we want interrupts to be enabled, which is located in the ADC IER register, the interrupt enable register. And we have a few choices. We have the EOC IE, which is the end of conversion interrupt enable. And we have the EOSEQ IE, which is the end of sequence conversions interrupt enable. We also have the OVRIE, which is the overrun interrupt enable. From my current understanding, this is the EOC, which is single conversion mode, or single conversion, which doesn't mean it's single or continuous. It means that it's going to do a single channel. And if you have the EOSEQ, which is a sequence, it is going to fire, the interrupt will fire when a sequence of conversions is completed, which means multiple channels are finished converting. So you can process all of the channels at one time in this interrupt. So if you have 2 channels, this will fire twice, so you can process each conversion separately. And if you have this one set and you have 2 channels, this will fire only once, and you can take care of all the channels at one time. The overrun is if there is a conversion happening, and in the middle of that conversion, another conversion wants to start. So this will fire if that happens. I'm not going to be using this one, but I will be using these. And since I only have a single channel, I'm going to be using this one in this particular tutorial. So the register is the IER register, and we're setting the EOC IE bit, the end of conversion interrupt enable. So when the interrupt has completed, it'll go straight to the function that handles that interrupt. We're at this point. Let's go ahead and put in that function, and that is the handler, the interrupt handler. The name that is used for this interrupt handler is very important, because if you don't name it exactly this, it will not find it. When the microcontroller fires the interrupt for the end of conversion, it's going to find itself within this particular function. So let's keep this here and get back to it after we do some more setting up for the ADC. Now there are 2 more instructions we need to add, and that has to do with the nested vector interrupt controller, the NVIC, which is actually a part of the CMSIS core library. We have to add the NVIC functions because all of the interrupts are handled by the NVIC. The 2 instructions you'll need is the NVIC enable IRQ, and we're going to be using the ADC1 IRQN. You notice that when I was typing this, You'll see the comp IRQ, and you have the one without the comp. And if you use the comp, all it does is it defines this anyway. So you can put in the comp if you want, and it'll do the same thing because it's just going to replace the comp with IRQN. And if you look at what the IRQN is, it is just equal to the number 12. That's it. You could actually put the number 12 in this spot, and it'll do the same thing. Let's go back to that. So let's put on the next one, NVIC, and this one is going to be setting the priority. And we're going to put the same IRQN in there, and we're going to set the priority to 0. And I don't have any other interrupts going on around here, so I can use a 0 here, but you want to change this number to what priority you believe that the multiple interrupts will have. And since I'm only using the ADC, I'm going to put it to 0, but if I was going to, say, set the timer interrupt or other interrupts, I could change the priority of these interrupts. And the last thing we need to put into the beginning of the main is we need to start the ADC. Just like we were doing in the while loop, starting it in the while loop, we're going to do that outside of the while loop because we're doing it in continuous mode. And we're just starting in the continuous mode, so it continually goes over and over again. And the ADC start is located in the control register. So now that we have it configured properly for continuous mode, interrupt enable, and we're setting the NVIC interrupt functions, we can go ahead and start putting the code into our handler. And in our handler, I'm just going to simply set the LCD, set the cursor location, because we're going to be, you know what, let me put in the initial thing we're displaying. We're going to send 2 lines, no delay, and we're just going to put ADC on the top and nothing on the second line. So at this position here, we want to put the number of the ADC, the value of the conversion. So we'll set the cursor location first, and it's 4 and then 5. So I'll put it 50, and we'll send an integer. And the integer to be displayed will be the ADC DR, the data register, because we should have that since the conversion has been ended or completed. And the max length, I'll just put 5 here. Should only be 4 digits, but I'm going to add 1 to it just in case. Let's go ahead and build the project and see if it still works. I have no errors. Looks like I have an error, and it says ADC DR. I forgot to the 1 after the C, so let's go ahead and do that. All right, let's try it again. Looks like I have another error. What is that one? And it looks like I have an issue with the NVIC set priority. It looks right. Oh, you know what? Priority. Okay, I forgot an R here. Let's put that R in. It almost looks like it's correct. Okay, now let's try it again. Okay, no errors that time. So let's go ahead and flash the microcontroller and see if it still works. Okay, the microcontroller has been flashed. Let's go ahead and see if it changes, and it looks like it's working fine. So now that we've tested the microcontroller and we know that it's working, let's go ahead and go back to the code and put this code in the .h file for the ADC. So I'm going to open up the ADC, and I'll make another function called setInterruptMode. I'm not going to be bringing anything in, I don't think. So let's just set our code block. And we'll take all the information from that we just created. Control X, cut, and we'll bring it into here. And I wouldn't be putting the continuous mode on unless I was using the interrupt at this point. I can't really imagine how I'll use it later, but at this point, I think I'm going to set it this way just so it'll be easier to put into the main program. I also probably want to set the non-continuous mode when I'm just doing standard pulling ADC conversions. So I want to take all of this out, and then I want to use the AND NOT to make sure this is a 0. So it unsets this particular bit. So it's in single conversion mode. So I'm going to call this polling mode. All right, so let's go ahead and save that. And in our main, we can just use ADC set interrupt mode. Okay, so let's go ahead and try this and see if it still works. We have no errors, so let's flash the microcontroller. Okay, the microcontroller was flashed. Make sure it still works. I'm going to show you how to bring in analog signals to the microcontroller on 2 different channels of the analog to digital converter. So you can convert channel 1, and in this case, I'm converting channel 4 as well. And I'm using potentiometers to show an analog signal coming into the microcontroller. The conversions for the analog to digital converter will be done through interrupts, and you will see that the conversions are listed as ADC1 and ADC4. So if I change the ADC1, which is the channel 1, you can see that the channel 1 does change, and the channel 4 changes independently of channel 1. I am only using these potentiometers in place of what would normally be used on these ADC channels, such as sensors. Another example would be having a completely different type of sensor here, like a temperature sensor, and maybe a sensor over here would be measuring the voltage of some part of a circuit, or a pressure sensor or something like that. In most circumstances, you'll need to use more than one channel on the ADC to bring in many sensors. So you're going to need to know how to receive those values from each channel separately. So let's go ahead and set up the circuit and go into the code. Oh, and I also added resistors here instead of just straight wires on one of them to show you at the low end how it affects the value, and on the high end how it affects the value. It doesn't go all the way up to 4095, and it doesn't go all the way down to 0 because there's resistance on each side of this. So it's as if this isn't getting the entire range of the voltage from the power rails. I would recommend putting small resistor values on either end so you're not putting the pin directly to the voltage extremes. Okay, so let's set up the circuit, and then let's see how we can accomplish this with code. Let's see what pins we'll need to use to access the channels for the analog to digital converter. Okay, we're currently using PA1, which is channel 1, ADC-IN1. That's on pin number 15. And because my potentiometer is so large, I need to go a few tie strips over. I don't want to use the F because that's not the ADC. So I'm going to use the ADC-IN4, which is the channel 4, and that's on pin number 20. So let's put one of the potentiometers on pin number 15, which is the ADC channel 1. Connect the two outer leads of the potentiometer to the plus and the minus rail. The other potentiometer to channel 4 of the ADC. And on this potentiometer, I'll be adding resistors to the power rail. Okay, let's start coding. The first thing we need to make sure is that we have the correct libraries installed or added to this project. The first thing we want to make sure is that the header files are loaded within the skeleton code. Is initialize all of the features that we're using, the ADC and the LCD. And we want to set up the LCD display. And if I want to put something on the LCD that explains what we're going to be showing, so let's go ahead and do that now. We're going to use the function that we created called send2lines, which allows us to put 2 lines of information on the LCD all in one function. This doesn't need to happen in the while loop because we only need it to display once on the LCD. Once it's displayed, it'll stay there. So I'll show the ADC1 on the first line and ADC4 on the second line. And I'm calling it 4 because I'm using channel 4, and that just indicates to me that the number next to it is going to be the channel 4. Now let's do the initialization for the ADC, and I want to invoke the interrupt mode. We have a special function for that. And the channel select that was created in the ADC tutorial, I can select channel 1. And because I'm ORing this, the channel select is using the OR bitwise operation. I can go ahead and use the same function to set up channel 4 as well. So this tells the microcontroller that I want to use channel 4 and channel 1 as channels to receive analog information. And then I can go ahead and start the ADC. Since we're using interrupts for the ADC, it's going to go to a separate function because it's not going to be polling within the while loop. Let's set up that function now. The specific ADC function has to be called ADC1 IRQ handler. And we're not bringing anything in. So when the ADC has completed a conversion, it will jump right into this handler. And one thing to note is that we're using, within the interrupt mode, we're using the interrupt end of conversion, i.e. interrupt enable, end of conversion. That will end each conversion of each channel. So it will come into this function when each of the channels are converted. So while the microcontroller is running, when it's converted channel 1, it'll go into this handler and run the code within it. And then when it's complete, it'll go back to the while loop. And when channel 2 is completed converting, it'll go back to the handler and then run the code. And as far as I know, there's nothing in the microcontroller registers that gives us a status of which channel it has converted. So we're going to introduce a new variable that tells us which channel it is on. So I'm going to introduce a new integer to the program called channel. And this will tell me which channel it is currently on. The channels will be converted in order of channel, the smallest channel to the largest channel, like channel 1, 2, 3, 4. So it'll do it in that order as it is converting, unless you change the scan direction. The scan direction is in the configuration register, CFGR1, and the scan direction is on bit number 2. So the scan direction bit means that upward scan from channel 0 to channel 17. It'll scan in that direction. If you set it to 1, then it will backward scan from 17 to 0. In this case, we're going to keep it as an upward scan, and that is the default. It's 0. So we don't need to change that register. So within this function, we want to increment the channel variable by 1. But when it gets here, this channel, since it's 0, the first time it comes in here, it'll be 1. So we want to first grab the data from the ADC. And you could be tempted to actually show the ADC data on the LCD within this function. But the problem with that is the LCD functions and putting things onto that display takes a long time. And it takes so long in microcontroller terms, not human terms, that many of the ADC conversions will have already happened by the time it puts one set of information on the LCD. So we want to just grab the data and then display the information within our while loop. So let's go ahead and grab the data. And we're going to have to create another volatile integer for channel 1 data. And we'll do the same thing for the channel 4. So if the channel is currently at 0, then let's grab channel 1 data. And it will equal ADC1 DR, the data register. We're going to do the same thing to channel 1. If it gets to channel 1, we're going to get the channel 4 data. And the reason why we're incrementing 1 is because we're only setting channel 1 and channel 4. If we had something in between this, like channel 3, even if channel 3 was after channel 4, it'll still get it in sequence of channel 1, channel 2, channel 3, channel 4. But if we only have it set up to do channel 1 and channel 4, it'll only want to get channel 1 or channel 4. It's not going to try to receive the channel 2 or convert the channel 2 and convert channel 3. It will only convert these two. So when it comes into the function for the handler, it'll start out with the first one being channel 1. The next time it comes over here to the function, the handler function, it'll receive the channel 4 conversion. This is only a variable. The channel variable is only a variable to determine what data is picked up at what time it gets to the handler. Now in the handler, the channel keeps incrementing upwards. So I'm going to add another condition. I want it to do it before these conditions because I want it to grab 0 or 1. If the channel is equal to 2, then I want it to start over. So because it's going to, after it does 1, it's going to increment the channel again, and it will be 2. So the next time it comes over here, it'll be 2, but I want it to be 0. So really it's just toggling between 0 and 1. So I think we're finished with the handler function. Now we can display the data in the while loop. So we have in line 1, ADC1, and line 2, ADC4. So let's go ahead and set the cursor location, 5 and 6. So 6th position on the line, and we'll start out with line number 0, and we're going to send an integer, and the integer is going to be channel 1 data, and I'll give it five maximum digits, and we'll do the same thing for channel 2 data. We'll go to line number 1, and we'll just show channel 4 data. So it's constantly putting the information to the screen, but it's doing probably a lot more conversions before it actually gets to the screen. So you're still going to see it very quickly, but the proper data should go into the right place on the LCD. So let's do a build and see if it works. Looks like there were no errors, so that's a good thing. So let's go ahead and flash the microcontroller and see if it works. Okay, the microcontroller was flashed. You can see we have ADC1 on the first line showing a value, and ADC4 on the second line showing a value. And if I change the first channel or the first potentiometer, you can see that the first ADC changes its value. And if I go to the next potentiometer, you can see that that also changes its value. One thing I didn't realize I did when I was putting the circuit together was I switched the leads to its negative and positive value. So the rotation that I use to turn it it goes in the opposite direction that I would think it does. So you can just change these leads. Like this lead would have to go to the negative and this one would go to the positive to get an intuitive rotation compared to the value of the ADC on the LCD. I want to show you a couple fixes that will enhance the output on the LCD display. In the previous videos, you'll notice that when I would, let's say, change the value, let's say for ADC1, and when I got lower in the value, you'll notice that there would be an artifact, a number here at the, let's say, 4th digit. You can see that I fixed that. And in the previous videos, what I would do is I would erase the number first, and then I would add the number, but that would cause the number to be very faint or almost transparent, and it would be very difficult to see the number. But there was an easier way to solve this problem, and I'm solving it within the actual library itself, where when it creates the string, or when it prints the string of numbers or characters, it would also print a space afterwards. So whatever was there in that location, it would be erased by the changed string of characters, or this changed next string of characters. This will really only solve the problem for numbers changing. Like if there was a number counting down, and the number counting down would be erasing as it counted down, and it would erase the next digit as it got that much lower. But if it was a string of characters, just regular string of characters, then it would erase the last one. It wouldn't erase the entire line. That's something that you still need to do. It makes more sense to have this feature for numbers counting down or numbers changing. So let's go ahead and see how you do this. Okay, we're inside of the LCD functions header file. And in the LCD send a string function, you'll notice that I added a character. I'm going to comment this out so you can see what happens if I don't do this. So I'm going to go ahead and go back to the main. So I'm going to build, so there's no errors, and I'm going to go ahead and flash the microcontroller. So let's go ahead and change it to 4 digits. And as you can see, when I go down, we're in the 500s now, but the 8 was left over as an artifact. So let's go ahead and put that back in, put that space back in. You'll see that change. So going back into the LCD functions, we'll uncomment that out. You know, the more I think about this, the more I think that we should actually not put it in here, because when we're sending a string, we want to send it without a space at the end, because we may have an instance where we want to maintain whatever is after this particular string of characters on the display. There may be something already displayed on the LCD, so I don't want to put it here. I think it makes more sense to put it where the number is. And my first thought is just to put a space right here. So what would happen if I just put a space after the string format of the integer? If I'm going to do that, I should also do it to this one right here, but I'm going to test it first for the integer and see what happens. There's no errors, and I think that's pretty obvious. You'll also notice that I have a +1 here in the max length of digits, and I did that because of a comment that I got on YouTube specifying that I needed to put a +1 here to reserve for the null character, but I'm not really sure if it's needed or not. I'm going to keep doing the testing, and if I see over time when I am having more digits being passed to the LCD, and if I see any sort of problems with it, I'll either take it out or keep it in, or actually maybe even add another one because of this space. So I'll just keep looking at it and see, just to make sure of it, you know, it works fine. So let's go ahead and test this out. We've already built the program, so I'm going to flash the microcontroller and see what happens. I'll adjust channel number 4 this time. It's this one right here. Yep, so it works. And so let's try it with a float. I'm going to go ahead and pass this number in as a float instead of an integer, and we'll see if it still works with a float after we make the changes. So back in the program, let's go ahead and put a space after the float and do a build and see if we have any errors. No errors. Let's go ahead and flash and see if it works. Actually, I need to still do the float. I didn't do that yet. So send an integer. I'll do that for data channel number 1. So I'll send it as a float. Send a float, floating point number, and then we want the floating point number to be displayed, so that's going to be channel 1 data. And then the max length of digits, I'm going to just put 5. I'll make it 6, because there may be a decimal in there, and I want to see the decimal happen. I'm going to comment this one out because I want to put this back in there. Let's go ahead and build, and then flash the microcontroller again. Okay, you can see that channel 1 has been changed to a float. It has a 0.0. Obviously, it has a 0.0 because there's no decimal in the output of the ADC. So let's change, see if it actually moves. Okay, it does not delete the artifact. So let's see why this does not work. So we put the space there, but really, after looking at it and investigating it, this is a floating point number, and there's going to be decimals, and there really isn't any artifact. The 0.00, the other 0 that happened after it, is just because because we're reserving that number of digits for this float. So you're always going to see those extra zeros at the end because the number really isn't changed. It is the real number, is it? So we can actually keep the floating point number just as it is. When you specify a number of digits, it's always going to show those number of digits, and you don't want it to show anything else because that's what you've created. So changing the LCD send to an integer, or send an integer, and putting a space after that really is the only thing we need to do. I'm going to show you how to create an external interrupt using a standard push-button switch. An external interrupt is where you use a pin of the microcontroller as an input and you provide a signal to that pin, and the microcontroller will handle the interrupt by going to a special function where you can add code when this interrupt is fired. This is an alternative to the polling method of testing the input on a pin within the while loop, the never-ending loop. The pin that will be used for input is pin number 50. Pin number 50 is port A, pin number 15. The switch in this case is pulled to ground using a 220k resistor. I added a small resistor here, which is only 330 ohms, just to add a little bit of resistance. And when the button is pressed, the pin will receive a high reading, which is on the plus rail. So when the button is pressed, it will go to this positive rail. When the button is not pressed, it'll go right through to the minus rail, which is pulled down to ground. When the button is pressed, it will increase, and you'll notice that it increases quite a bit on each button press, and that's because the button bounces. And the interrupt is extremely sensitive, and we are configuring the interrupt to increment a variable for every rising edge. So this particular type of experiment would be better on a non-mechanical clean signal coming in. You can eliminate the bounce in the interrupt, but that will not be the subject of this particular tutorial. The circuit is actually the same as the previous push-button videos. We're going to add a resistor to that pin pulled down to ground, so the pin is not floating. When the button is pressed, it will connect to the high side, or the plus rail. The first thing I'm going to do is just include my standard include files. And I'm going to include the LCD functions. And we want to set up the port A, pin 15 as input. So let's go ahead and do that first. And this is stuff that we've already learned how to do. I'm going to use the reset clock and control register and the advanced high performance bus, GPIO-A enable. Now we're going to change the mode register for the GPIO-A to serve as input. And we want pin number 15. And we will also want to set no pull up, pull down, since we're doing that externally anyway. At this point, we might as well set up the LCD. And in the beginning of this, I'm going to put a not exact time delay, and I'm just going to put maybe 10,000 in here. And what I'm doing is I'm creating a very short time delay before the LCD initializes. I've noticed when I plug in the circuit for the first time, the LCD is not really ready until a little bit after the microcontroller sends this initialization code. So I'm going to add just a little bit of time delay, give the LCD some time to get ready. I'll set up the display, and I think I want to add some information to the display. I'm going to call it just A15, since it's a description of port A and pin number 15. In the second line, I'm not going to put anything. Let's stub out the interrupt function first, just so we can... Actually, let me do the NVIC first. The nested vector interrupt controller. And we're going to enable an IRQ, which is going to be the external interrupt. And we have some choices here. We have 0, 1, 2, 3, and 4 through 15. And because we're accessing the pin number 15, we're going to be using this particular interrupt. And now we need to set up the priority for the same external interrupt designation, and we're going to set priority to be 0. Priority, you have the option of going from 0 to 3, and 3 being the lowest priority, 0 being the highest priority. I'm not sure if that is actually correct, but I'm going to assume that is correct at this point, and I'm not using more than one interrupt in this case anyway, so it doesn't really matter how I set the priority. So now let's go ahead and stub out the void. And the reason why I wanted to do this first is because This right here actually is part of the name of the function for the handler. So I'm going to go ahead and copy that without the n at the end. And these functions for interrupts have to start out with void because we're not returning anything. We wouldn't be able to know what it's returning anyway, so we don't need to worry about that. I'm going to put in the external interrupt 4 through 15, IRQ, and then handler at the end. And then we're not bringing anything into this, and just like the return, we wouldn't really have any access to put parameters in that I know of, because the microcontroller handles calling this particular function when the interrupt is fired. Now let's get into the external interrupt specific control, how we control the way it interacts with the pin and how it picks up a signal. The first of these is the interrupt mask register, and we need to know which line, channel, or pin we're using. In this case, we're using pin number 15. And in this case, because it says 0 is when line X is masked, we want when the line X is not masked. So we want 15 not to be masked. So let's go ahead and set the mask register bit number 15 to a 1. The next control we need to consider is the rising trigger selection register, where we determine the way we pick up a signal is on the rising edge. The way we set up the circuit, the pin is idling at 0 volts. So it constantly sees 0 volts until we press the button. And at that point, the signal looks like this. It's bouncing, and then it finally reaches its 3 volts. It's going to find every single rising edge that you're going to be able to give it. And when a button press happens, you'll notice that there's a rising edge here, there's a rising edge right here, there's a rising edge here, and there's a rising edge here. Different buttons with different mechanical properties may have different outcomes. But the buttons I'm using have rising edges. It's going to capture every single rising edge that it gives you. If you want to put a push button on a pin using an external interrupt, then you're going to have to figure out a way to determine a true button press. So with that out of the way, let's go ahead and add the external interrupt rising trigger selection register. And to enable it, we're just going to put a 1 in bit number 15 for that register. Another register that we may have to consider is the system configuration register that controls the external interrupt configuration. And in my experiments, I've noticed that this doesn't really have any effect at all. I've commented it out and ran it, commented or uncommented it, or invoked it, and the results are exactly the same. So I'm going to put it in anyway, just because it doesn't seem to harm it any. So the way you use it is they have the configuration for each port, but you need to specify which pin, and that is what position or bit position that you use the specific bits within those positions. And you have many choices. You actually have 4 choices for the external interrupt configuration. You have the 1, which is from 0 to 3, 2 from 4 to 7, 3 from 8 to 11, and the last one, number 4, is from 12 to 15. And we're going to be using number 15. And we specifically want the PA. So it's going to be 000 in those bits. So let's go ahead and configure that one right now. And you'll notice that there is an array of 4 positions here. So it's going to be from 0 to 3, and ours is going to be the 4th one. So it's 3 with an 0 indexed array. And we're going to select number 15 for PA. And the reason why it doesn't make a difference from my testing is because it's all zeros anyway, so it's going to be at the reset value. Now let's go to the function for the handler. This is where the microcontroller is going to take you when the interrupt fires. But you'll notice that it'll fire for all the lines between 4 and 15, all those channels or all those pins. So we need to determine which pin is being fired at the time. And the external interrupt pending register has that information. We are interested in the PR15. If we see a 1 in that bit, then the selected trigger request occurred, meaning that particular line has received a rising edge. with the way we're controlling it in this particular program and circuit. So let's go ahead and test for that bit. If the 15th bit in the external interrupt pending register is true, then it found a rising edge. So now we've tested for the bit, and if it is true, we'll run this code. We have to reset this bit after we know that it has actually been fired. So to do that, we just do, or put a 1 in that same bit. It seems odd to do this because it already has a 1 in it, because it wouldn't have gotten here unless it had a 1. But according to the datasheet, the request is reset by writing a 1 in the pending register. The datasheet really isn't very clear about this, and it took me quite a while to figure this out. But after doing some testing, if you don't actually add this line, as per the datasheet's recommendations, it really doesn't work. So this is actually needed. So in this particular case, I want to know if it's been fired or not. So I'm going to add another variable, and it's going to be a counter. I'm going to use a volatile int because I want it not to be optimized out. And I'll call it port A pin 15 counter. And right in here, I'm just going to have an increment by 1. So if it got to this location and it actually is the line number 15 has been fired, then this counter should count up. And I don't want to put anything else in this area because I don't want it to cause any delays. So I'm going to keep this very short. Just have this, I could just have a flag in here stating that a rising edge was found, and then I can deal with it in the while loop. But I just want to see a counter, and that this is easy enough to put it right inside of the interrupt function. So in the while loop, I'm going to display that counter on the LCD. We'll send it to the LCD as an integer. So everything should be good. Let me go ahead and build, and let's see if everything is good. Looks like we have an error. Let's take a look. RTSR, it's probably not the way to spell it. Oh, I see, because I have an underscore here. Put a hyphen. Should work now. Build it again and see if we have any errors. No errors, so I'm going to go ahead and flash the microcontroller and see what happens. The microcontroller has been flashed, and you can see that we have the correct label, A15:, and has a 0. Let's see what happens when we press the button. You can see a number 2 appeared, 3, 4, then 7. So it is getting every rising edge whenever I press the button. And you can see that it is also picking up all the bouncing. Okay, so that is how to use the external interrupt to receive a digital signal from a pin. Let's add another button to the microcontroller so I can show you how to separate those two button presses, those two interrupts. And it's going to happen within the same interrupt handler, but on a different line or a different pin. The pin that I will use is located at pin number 44. Pin number 44 is here, port A, pin number 11. Let's add another push button to pin number 44, exactly the same way we did with the other push button. Now that we've added the button to the circuit, I'm going to go ahead and add another line to the LCD that describes what we're going to be showing. And that's pin number 11 on port A. And let's go ahead and get the pin 11 on port A set as an input on the GPIO. We don't need to enable the port again because we've already done that here. It looks like I actually did something wrong here. I'm only specifying 5, not 15, and it probably looked like I was doing 15. So I'm going to change that. Okay, so that's correct. And now I want to duplicate these two for the pin number 11, the interrupt mask register and the rising edge register, the rising trigger. So I'm just going to change these to 11. So now we're enabling pin number 11 on port A for input, and we're adding the interrupt, external interrupt control parameters for pin number 11 as well, or line number 11. This doesn't have to change because this is good for lines 4 through 15. And in here, the handler, it's going to handle everything between 4 and 15. So we need to duplicate this one. But we also need a new counter too. So let's make a counter first. And we'll just call this one port A pin 11 counter. I'll duplicate this one. I need number 11 here to test the pending ready bit. And we'll do this one over here to reset that. And we'll use the new counter. And now we need to display the counter in the while loop. So this is going to go on line 1, and we'll use the 11 counter. So this is all that should be needed. Let me go ahead and build and see if it builds correctly. Looks like it worked. The microcontroller has been flashed, and when I press the pin number 15 button, let's see what happens. Okay, so the display is showing the counter going up when I press the 15. And when I press the pin number 11, let's see what happens. Okay, so it looks like we have a successful implementation of an external interrupt using push buttons. One major caveat to using the external interrupts and assigning pins to these interrupts is that you can only use a single port for the line that you select. Say you're selecting line number 15. So the pin associated with 15, the port that you select, like port A, and you select pin number 15. You cannot use port B, pin number 15, or port C, pin number 15. You can only use port A, pin number 15. If you remove port A from pin number 15 and you use port B for pin number 15, then you're able to do that. You can see in this figure 22 external interrupt event GPIO mapping that the external interrupt number from 0, 1, all the way to 15, you can see that they're all tied. All the ports are tied to a single interrupt line. So you need to choose between which port that you want to use for that particular line. In these videos, I've only used port A. And in my tests, I've only been able to get port A to work. I'm not actually sure why. I've done many tests with port B, port C, port F, and I've connected them to internal interrupts, not interfering with port A and the pins that I'm using. So I'm not actually certain if I'm doing something wrong, or maybe that I have a damaged chip on my breadboard, but I was successfully able to do it with port A. So for that part of the experiment, I think it was a success. But because I wasn't able to use a different port, I failed in that respect. And I was doing the testing for probably about a week now, so I'm not going to continue with the tests for a different port. I think I've done a sufficient job in covering interrupts in general, but I will probably revisit interrupts at a later time because I want to start to cover other features of the microcontroller. If you're able to get another port to work on a different line or different pin, let me know in the comments. I hope this helps. Thank you for watching. It's time to liberate the LCD. I'm removing the LCD for a few reasons. I want to have more space to add more devices, so I'm going to need the breadboard real estate. I need more space and more tie strips to be able to do what I want to do. The LCD also doesn't allow for enough presentation of information while doing my projects. I only have so much room on the LCD to be able to show what I need to show. And the LCD is mainly used for a display for the end user of the final device anyway. It's not really meant to be used as a debugging device, although it works for that. But my biggest reason that I want to remove the LCD now is that the circuits that I add to the breadboard, I want to make them as simple as possible for the beginner. My whole approach in teaching and learning myself is to work with the simplest and most minimal circuits as possible. So now we have all of this free area, breadboard real estate to use for future projects. And I'm not really too keen on these wires hanging around on this location of the breadboard. This was created because we needed space for the breadboard on this area for the LCD. So I'm going to add the wire connections back from this power rail to this power rail like I had it before the LCD was installed. And I'm going to remove these wires so I can clean up this top area here. And we'll be back to a very basic and simple circuit. Remove the two wires, pins 64 and 63, to the unconnected power rails. And now connect the two remaining power rails together. The circuit should now look like this. Pin number 1, which is a positive power connection, should be connected to the positive rail. The analog to digital converter power should be connected to the power rails. The other power connections, 31 and 32, should be connected to the power rails, and 64 and 63 should be connected to the power rails. All the power rails are connected together from this portion. This breadboard is connected to this breadboard's power rails using these two wires. The power on this part of the board is being provided by this power rail, and then this power rail is connected to the remaining breadboard with these two wires. So now all of the power rails have power going to them, and the entire board can be powered. The main power, of course, is coming from the ST link going to these two main power connectors. When you've finished installing the STM Studio, you'll be presented with a screen that looks similar to this, where you have a variable viewer here, and you're going to have the variables listed in this location, and you have the option of how you want to receive the information from the microcontroller using JTAG, the SWDIO, the SWIM, and the ST-Link. The ones that I'm going to be using, or the one that I'll be using, is the ST-Link SWD. I'm not going to get into this program in any depth right now, because as I do the projects, I'll show you how to use this program. And in this video, we will start with a quick example of the ADC, the analog to digital converter, and the potentiometer like we did before. And we will monitor the data register of the ADC using this program here. So let's go ahead and set up the circuit for the ADC, the potentiometer, on port A on one of those pins, one of the port A pins, like we did before. Add a potentiometer to pin number 15, and I'm adding 330 ohm resistors to each high and low leg of the potentiometer to provide a little bit of protection for the pin on the microcontroller. Okay, I'm starting with some skeleton code here, an empty project. Make sure that when you create your project, you'll have the adc.h in that project. Okay, let's put in the include files. This is our standard include. Include the adc.h file. So let's initialize the ADC. And we're going to set it up as the interrupt mode. And the channel we're using is channel number 1. And to get this ADC to start collecting data, we have to use the AD start bit in the control register. And the interrupt mode, look at the ADC file. In the interrupts, we are using the ADC1 IRQN. So I'm just going to copy that so we can create our function. Void ADC1 IRQ handler, void. And inside this, I want to put this into a variable because I want to view this variable in the STM Studio. So we'll create a volatile int. We'll call it ADC data. And over here, we'll take the ADC data and assign it the ADC1 data register value. So whatever is in the data register, we'll see it in this variable. So we can monitor this variable in the STM Studio program. So let's go ahead and open up the STM Studio. Well, first we need to build the file. Let's see if we have any errors in it. We have no errors. So we can go ahead and flash the microcontroller. So the microcontroller should be flashed. Now that we have the microcontroller flashed, we can go ahead and start the STM Studio. And the first thing we want to do is we want to import a variable into this location here. So you can press the right button, import, and at the ellipsis, just click on this, the bin file, and you want to use the ELF, the ELF file. And the ELF file has all of the information that you need within the program that we just created. And the one we want is the ADC data. If you remember from the file, this is the variable that we created, the ADC data. Going back to the STM Studio, once you've selected this, you can click on the import, and you'll see that it added it here, and you can press close. And you also want to send this variable to the viewer. You can have many variables in this location, and you can specify which ones you want to actually view at the time. So you press the right button and you send to var viewer. You're not going to see anything right here because the potentiometer is probably a little bit too high of a value, but also we haven't started playing it yet. So I'm going to go ahead and put the lower value at 0, put the upper value at 5,000 because I know it's going to be 4,095. And that's going to change your vertical axis. You can go ahead and play it, and you'll see that we have data at between the 2,000 and 2,250 range. And if I go to the potentiometer and I start changing the potentiometer, you'll see that it also changes in the variable viewer, that particular variable. You can also look at it not just as a curve, but you can look at it as a bar graph and as a table. So you just see the value here, which is what you would have seen in the LCD. So from now on, in the tutorials that I'm going to show and the projects that I include in this tutorial series, we'll be using this resource to view the variables that we put into the programs. This resource will be indispensable when we're working on new projects. We will be able to add quite a few variables to our programs and peer into how the program is performing as it runs on the chip itself.